Santosh, can you hear me?
Yeah, I just connected my earphones. Good morning.
Yes, good morning. Santosh, how are you?
Good, how are you, Professor Yusuf?
Okay. Managing.
That was a surprise. Nirmala, I never noticed that you are the chairman.
Would you like to test your slide projection?
Yeah, I can.
Okay. Yeah, full
Can you
screen.
see that?
Yeah, this is good. Can you make it
Yeah.
full screen? Yeah.
Let me check the pointer thing.
Yeah, sure.
Yeah.
Yeah, quite good. Yeah. Perfect.
Santosh, I'll be missing your talk because me and Suresh is sitting for faculty selection.
I know.
So we have to take turns.
Yeah. So, after mine is Suresh, right?
Yeah. I think after yours is Suresh, and then after Suresh is me. So we will take turns there.
Okay. So when are you back?
These organizers have done a good job. They have put all magneticians together.
Yes.
But luckily, physically, we are apart. Otherwise, magnetostatic energy would have been very, very high, you know.
I mean, it's unfortunate that it is an online meeting.
Online thing. Yeah.
Yeah. This actually, this needs physical interaction, presence, and strong face-to-face interaction, you know.
Yeah. You know, Yusuf, this is my alma mater as well.
Oh, I see.
Okay.
I studied in this college for my 11th, 12th. That time it was called B degree.
Yeah.
Then I did my BSc also from Fatima College.
Great. Okay.
So we have a colleague from there, Manoj.
Yeah.
Okay.
So it's my alma mater. If it was an in-person meeting, you all had an opportunity to come to my house also. It is in the maybe hardly 4 kilometers from the college.
Okay.
I see. Yeah, I could guess some correlation, you know. Anyway, good. So how is this? This is supposed to be a good one, right?
It's a good one, going on well. Yeah. So it's a good one. Yeah. I mean, they could get a lot of good speakers, and yeah, it's well.
No, I mean to say in terms of college education, teaching.
Yeah, it's a good college. It's a good college, yeah.
How many years since it has been established?
I think it should be in 1950, somewhere around that time. I think that's what somebody from the college can tell. It's 1950, close to 1950. Let me see who is there from the college.
Professor Sunil Thomas is there, I think.
Sunil, are you there? Yeah, if I'm correct, 48, 49, 50.
Okay. Okay.
But my memory.
Okay.
See, that time after 10th, you go to college, right? Nowadays, you study 11th and 12th in the school.
Yeah.
Yeah.
So after 10th, I went to this college.
Yeah, our time, both options are there. One could go to college or one could go to school. So I prefer school, you know.
Oh, okay.
Morning, Suresh.
Good morning.
Oh, hello. Good morning.
Yes. Very good morning.
Very good.
So I will be able to join only a little late.
Okay.
For the talk, we have some meeting.
Yeah. Professor Anil told us.
But other member has already joined. So how it is possible? Other member has already joined, I believe.
No, other member will leave soon.
I see. Oh, okay. So phase manner. Okay.
So we are actually going to replace each other. So.
Oh, I see.
Okay.
That he didn't disclose.
No, actually, we were doing marathon from yesterday. Yesterday we had from 10 to 5 o'clock.
Yeah.
Okay,
Sunil told
ma'am.
us,
But the other member has already joined, so how it is possible? Other member has already joined, I believe.
No, other member will leave.
Hi, ma'am.
hello.
Can we start? Can we start?
No, we are actually going to replace each
Yeah,
other.
I think I've asked
Right.
Professor Suresh
That
if he
is
wants to
the
test
mic
his
on.
slides.
Yeah,
All
yeah.
others
Yes,
have
yes.
tested.
Okay,
Huh?
okay, ma'am. Okay.
We were doing marathon from yesterday. We
Professor
had-
Suresh, can you please check your slides once if
Yeah,
you
yeah.
wish?
This
Yeah.
has to be unshared. Okay.
Yeah,
Shall I
yeah.
try?
Yeah, please try. Yeah, this is good. Yeah. Quite good. Thanks. I think we are only left with one more speaker. I have not seen
No.
him, Dr. Shinai Thomas.
Because
If
we are
he
already.
wishes to, yeah, otherwise we can start the session. Yeah.
Should I start sharing or little later?
I will ask the organizer to start.
Ma'am, we will start from outside then.
Sure, please do
Yeah,
that. Yeah,
thank you,
thanks.
thank you.
Thanks. Yeah.
Good morning to one and all. It is my great honor
good.
to welcome you all
I think
to the
we are
fourth day
only-
of ICMPMA 2022. Today we move on to the sixth session of our conference. The topic for today's talk is magnetic materials. To chair this session, we invite Dr. Nirmala R., who is working as professor at the Department of Physics, Indian Institute of Technology, Madras. She obtained her PhD in physics from the Department of Physics, IIT Madras in 2003. Then she worked as a postdoctoral fellow at the Department of Condensed Matter Physics and Material Science, Tata Institute of Fundamental Research, Mumbai, and at the Solid State and Structural Chemistry Unit, Indian Institute of Science.
I think you have got cut off.
Sorry, ma'am. We'll continue.
Sure, thanks.
She is also visiting scientist at Seoul National University, Seoul, South Korea. She has over 100 publications in referred journals. Her research interests include magnetic, thermal, and electrical transport in rare earth intermetallic compounds and correlated oxides. Dear ma'am, we are honored to have you here. I warmly welcome you all to start the session.
Thank you so much. I also thank Professor Sunil Thomas and all the members of the organizing committee of this ICMPMA 2022 conference. It's my pleasure to welcome you all to this session 6 on magnetic materials. I am sure we have very energetic and recharging session ahead. In this session, we have 5 talks, 1 plenary and 4 invited. And this will be followed by the poster session, which goes little later after lunch until 2 p.m. So first, let me welcome Professor S.M. Yusuf, presently Director, Physics Group of Baba Atomic Research Center at Mumbai. Professor Yusuf, as you know, is a very well accomplished experimental condensed matter physicist. And he's a fellow of both the Academy of Sciences, Indian Academy of Sciences and National Academy of Sciences, India. And after his PhD, he spent a postdoctoral term at Oregon National Labs, USA, with a US DOE fellowship. And he was also a visiting scientist at the Institute of Material Science in Spain. And he is well known for his work on low dimensional magnetism, in addition to the work on bulk magnetic materials and neutron scattering work. And he is currently serving as a vice chair in the Division of Condensed Matter Physics in the Asia Pacific Physics Society. And also he is a vice president and board member of Asia Oceania Neutron Scattering Association. And he is also vice president MRSI and INSA nominated member in the International Union of Crystallography, and he serves in many committees at the national and international level. And he has many honors. And out of that, I'll mention a few. MRSI Distinguished Lectureship Award, P.K. Iyengar Memorial Award given by the Indian Physics Association, Raja Ramana Prize lecture from JNCSR, DAE Homi Baba Science and Technology Award, and MRSI Medal Lecture, and also the DAE Group Achievement Award. And he works on many systems, okay? And recently, he has done quite a lot on this negative magnetization or magnetization reversal phenomenon. And he has tested this on various magnetic systems. So we have a very well-known review article written by him along with a student. I think he is going to give us a summary of that in addition to the new work. Welcome, Professor Yusuf. We are really honored to have you. Thank you.
Thank you, Professor Nirmala, for your very, very kind introduction. I hope my slide is visible.
Yeah, yes.
Yeah. And it is really honor for me to give this talk. And in fact, this is a very great initiative from this autonomous college. And I must thank the organizer, particularly Professor Sunil Thomas, for the kind invitation. And today, as Chairperson Professor Nirmala already pointed out, that the theme of my talk is based on the negative magnetization phenomenon, which we have been pursuing over several years. Just one second. Yeah. Yes, so this is the title of my talk is Physics of Magnetization Reversal Phenomenon. We have been working on several class of magnetic systems, as Professor Nirmala already pointed out, starting from 1D to 2D magnetic systems, quantum magnets, and spintonic materials. Of course, this magnetization reversal, the negative magnetization, which I'll be talking today, it forms a part of the spintonic material. And we have also investigated a lot in the area of molecular magnetic materials, besides multiferric material and effect of large magnetocaloric effect in various rare earth-based magnetic materials, and also nanostructure materials and battery materials. In very recent time, we have started working on particularly sodium and lithium-based battery materials. But today, I'll be concentrating the one particular phenomenon which we are passionate about more than 1 decade, that is called the magnetization reversal. And this particular phenomenon, actually phenomenologically, it was pointed out long back. In fact, Professor Neil, in his Nobel lecture in 1970, he did mention that there could be a magnetization reversal of spontaneous magnetization reversal in various, particularly with regard to ferrites. That time ferrites were well known in terms of magnetic material. And it was, of course, prior to that, he published papers in 1948 and later a review article in 1955. So, but that was phenomenological. But it so happened after that this particular phenomenon did not get any attention, and particularly from an experimental point of view, though I must say that it was observed. And if you, when we look at the literature, this is what Professor Neil suggested, that in case of ferrites, there could be various ways one can have this magnetization. Here you can see that net magnetization over this, it is negative, and here it is positive. And in fact, our work started with when Amit Kumar, he was doing PhD with me, and we published the very first paper in this PRL, followed by APL and so on. And this material, this is in this kind of ferrocyanide. And where you see the magnetization, DC magnetization as a function of temperature while cooling. Here it is positive, but it goes all the way negative and remains negative. So this is like, you are getting magnetization, net magnetization, which is aligned antiparallel to the externally applied magnetic field, which is a new phenomenon. And after that, we started working on it, looking at the literature status, and we could see that there are several reports, several observations, but somehow this was not highlighted. Very often it was suggested could be artifact, or sometimes the authors remain silent about that observation. As chairperson already rightly pointed out, we have been working on this. As you see, there are many fundamental papers, but today's talk, I will not be more focusing on the very recent papers, 2021 and so on, and 22 even. But based on the prior work, we wrote this review article, and I can claim that this is the first experimental, some kind of establishing that this fact is a genuine effect. There is no artifact, and this is one particular kind of magnetic phenomenon which needs much larger attention. And if you see here that the number of papers, which is this particular review article, the way it is cited as of 22, this is 21, 22, I have clubbed 173, and over the years it is, of course, it is adding. And the papers which are supporting to this fundamental paper, they are also well cited. For example, this APL paper 105 times and so on. Now, as I said, this phenomenon has been observed in various classes of magnetic materials, either it is perovskites, either it is molecular magnets, either it is ferrites, and very recent results I will even show from the garnets. Now, first, let me talk about this, the earlier work, where in this copper manganese iron based molecular magnets, and there we have done neutron scattering, we have done mean field calculation, we extended the results in collaborative mode, even XMCD. So here, under this is a kind of crystal structure. How do you see the magnetic atoms are sitting at this corner? This is like a double perovskite kind of structure. It is the bridged by nitrogen and carbon atoms, the magnetic atoms, and the internal molecular field seen at the copper side can be written like this. Similarly, for manganese, it can be written like this, and also at the iron side can be written like this. And this is the molecular field coefficient, and we could calculate the sublattice magnetization using this Brillouin function, and with all these numerical values based on which is relevant for our system. And these J values are determined from this magnetization study. And by doing this, we could calculate the magnetization as a function of temperature for individual sites, iron, copper, and manganese. And that the net one, the green one, is the net moment as per the formula unit. And this is our, so this is the mean field calculated. And when I superimpose this mean field calculated along with the experimental, you see very nice matching. In the sense it is able to reproduce this. So mean field understanding of this phenomenon we could achieve by doing this kind of mean field calculation. We also extended this to know what is the effect of external magnetic field. And as you see, as you increase the magnetic field, this magnetization reversal could be stopped and it remains positive, which is more conventional. And this is again mean field theory calculation under field. It also tells that. See, when you do mean field calculation under field, so we take external Zeeman energy as well as internal field both. But for neutron diffraction case, which I showed earlier, there we take only the internal field because externally we did without applying any magnetic field. This has been observed even nanoparticles. Here you see the TM image and this single nanoparticles of the chromates. And here, what you see here, basically the core part and the surface. And surface, you see the structural disorder. And this structural disorder, atomic disorder at the surface of this nanoparticle, what you see here, 4 nanoparticles on the copper grid, 1, 2, 3, 4 nanoparticles. But you see the defects on the surface, and this kind of structural defects, it gives some kind of magnetic disorder state as prone to spin glass type of. So antiferromagnetic core and spin glass like disordered magnetic state at the surface. So that creates the interface, and which also shows this kind of magnetization reversal, the top one. But interestingly, along with the magnetization reversal, what you see another one, what is called exchange bias. And exchange bias also showed the reversal property, and there is a one-to-one. It's a mirror image of that. And as you all know, that exchange bias is very, very important in magnetic memory devices. And so to say, the magnetization of this polarity reversal, which I will be touching upon at the end of my talk, what is the relevance of this magnetization polarity reversal and exchange bias reversal. This we have observed, for example, in this perovskite NdMnO3. Here you see the magnetization as a function of temperature, different field. At lower field, you do see magnetization negative, but at higher field, it remains positive. And AC susceptibility also shows the signature of phase transition, both at this magnetic ordering temperature from paramagnetic to here it is, you can say ferrimagnetic, and also at the compensation temperature. And Neutron depolarization study also gives the signature that at this temperature where this polarity reversal takes place, the recovery of neutron beam polarization. I will be touching upon this part more detail in next example. And if you, when we calculated the entropy change, magnetic entropy change, what we see across this compensation temperature, there is a polarity reversal of even delta SM, magnetic entropy change. And as you know, this part, this positive part corresponds to the magnetic cooling, whereas the negative part of minus delta SM corresponds to magnetic heating. So this is like you get both magnetic cooling and heating out of the same system. We have done detailed neutron diffraction experiment down to 1.5 Kelvin. And by analyzing this, what we see, the magnetic structure above this above this temperature, 15 K, where there is a compensation, where there is a spin, the reversal, magnetization reversal takes place. There the magnetic structure where you see the ordering of only the iron moment in the manganese moment means tensile metal, but below this temperature, which I show here at 1.5 Kelvin, you see ND also gets ordered, and that is ND also gets ordered, and this one is outside. Yeah. So the ND also gets ordered, and here it is, but you see the iron, as far as manganese is concerned, it has got the antiferromagnetic along crystallographic A direction and ferromagnetic along crystallographic B direction, but ND orders with the ferromagnetic component along minus Y direction, minus B direction. So this kind of, so basically ND ordering and ND the way it is ordered. So you see that essentially the antiferromagnetic component is there. So when we look at the net moment, when you look at the net moment, which is the green one, which shows the magnetization reversal. This is what is reflected, and the green one is the net one. Now, along with that, we see structurally also there is structural distortion taking place at the same compensation temperature, which is evident in the lattice constant as well as bond angle measurement. Now, I show another example from the this is a ferrite system, where the cobalt chromium iron based. Here again you see the similar observation of magnetization reversal very clearly, but field dependence also seen. And here I want to tell you, this is for one of the composition. This is particularly for 0.15 in this series, but you see the full series data. So you see only for particular composition, that is 0.1, and the blue one is 0.15. For these two composition, you see reversal, but not for other composition. That is basically, you need to have the balance between different magnetic sublattices, you know. So that means you need to have right kind of composition, balancing, then only you will see this behavior of magnetization reversal. we have used polarized neutrons in so-called neutron depolarization study, where in Dhuba reactor we pass polarized neutrons through this kind of magnetic sample. And what happens while you have magnetic domains or magnetic clusters with net moment, and you pass the polarized neutrons with all spin having up, if there's a net moment of ferromagnetic domain or clusters, then there will be rotation of this neutron polarization. So in the outgoing channel, you will see the change of neutron polarization. Okay. By doing that, essentially, this is a technique where we directly see the mesoscopic object. Here it is the magnetic domains. Now, here is the magnetization as a function of temperature. You see this, this is the magnetic ordinary temperature, Curie temperature, or rather nil temperature. And then magnetization maximum, but then decreases, goes to 0. This is the compensation temperature, and then goes to negative side. Now look at the below, the neutron depolarization study, that is neutron beam polarization, means transmitted neutron beam polarization. In the paramagnetic state, and spins are all disordered, there is no net internal moment, as a result, there is no change of polarization. So the neutron spin cannot rotate. That's why it is same as the incident beam polarization. But as soon as these ferromagnetic domains, they are formed at this magnetic phase transition temperature Tc, we see the decrease of neutron beam polarization, because polarization is rotating, and it is maximum rotation is there where maximum magnetization, one-to-one correspondence. And then when the magnetization decreases, so rotation also decreases, so less beam polarization. But very interestingly, at the compensation temperature where magnetization is 0, their neutron depolarization is 0. That means the magnetization is a bulk technique. Now we get magnetization, as you know, from the entire sample. You have taken 100 milligrams of sample. So you do not know at what level this cancellation is taking place. So, but net moment is 0 in terms of DC magnetization. But this neutron depolarization study, which is a mesoscopy length scale, which looks at the magnetization at the domain length scale, domain over the domain. So it only tells you that at this temperature, even all individual domains, they have net, each and every individual domain has got 0 net magnetization. That means domain has lost its magnetization at this temperature. This is the direct evidence of that domains are having 0 magnetization at this particular temperature, but not above or below. We'll also, after this, we'll also show the neutron diffraction data, where you will see that even this cancellation of moment is taking place at the unit cell level, magnetic unit cell level. So as you know, within the domain for students, how many magnetic unit cells are there? Even the cancellation taking place at the unit cell level, that comes from neutron diffraction, and neutron depolarization said the cancellation is coming from domain level. Obviously, if unit cell has no moment, so domain has no moment, so net magnetization, bulk magnetization measurement also 0. So this is what I want to bring the clarity. Now from the neutron diffraction, as you see here, that when we cool it, the magnetization, the intensity grows, and this is the intensity of individual Bragg peaks. And you see the tetrahedral side. This is the tetrahedral side magnetization as a function of temperature measured by neutron diffraction. And red one is the octahedral side. But you must see here one interesting observation, that this is the magnetic ordering temperature where you see, okay, so-called TC in DC magnetization. Study what you see in magnetization measurement. So there, neutron diffraction tells me that only octahedral side gets ordered, magnetically ordered. There is a magnetization, spontaneous magnetization moment is forming only at the octahedral side. But tetrahedral side magnetic ordering taking place at much lower temperature. So this is definitely a clear deviation from the mean field concept, because as you all know, the mean field states that only once one magnetic side gets ordered, it produces internal field, and it will, other side will also get order. That is usual, but that is not happening. But one more interesting point, when this tetrahedral side getting ordered, we see also second jump in terms of growth of magnetization of the octahedral site. So, and the green one is the net one, considering both octahedral and tetrahedral. You know, in ferrite structure, how many octahedral, how many tetrahedral sites are there, and you have to also take the cation concentration and so on. So net one is definitely showing the magnetization reversal and zero magnetization at this temperature. So this is a microscopic picture of this magnetization reversal. I show now, this is one of the results of my student Deepak, along with my colleague Amit. See, this is in physical materials 21 we reported. And here, what you see here, this, this is disturbing. Yeah. So here again you see magnetization as a function of temperature. What you see, the compensation temperature, negative magnetization, but with increasing field, it remains positive. Specific, it also shows the kink at magnetic ordinary temperature and also at the compensation temperature, and where compensation temperature we show here in large way. Now, again here we show that the polarized neutron study, as I shown for the other cases, we do see recovery of the neutron beam polarization full at this point, and maximum neutron depolarization where you have maximum magnetization. But interestingly, we see the exchange bias, and you see the exchange bias both with regard to the field axis and with regard to the magnetization axis. And there is a reversal, polarity reversal of exchange bias at this compensation temperature, both in field axis and the magnetized axis. So here I like to tell you that over recent years, what we are trying to do, since we have already established the magnetization reversal phenomenon, now we are trying to see the cross correlation, whether the magnetization reversal or magnetization compensation has any consequence with other physical properties. And that is indeed is shown here that exchange bias is very much coupled here, one-to-one correspondence. Even here you see the dielectric constant. Here also you see there is this is a compensation temperature, you see the one-to-one correlation. So this kind of novel correlation of different physical properties across this magnetic compensation temperature are established in recent time by us. Here, you again, I will not go into details. This is a magnetic structure to explain the microscopic origin of magnetization reversal. The DC magnetization we have also modeled using the Cook's model, where we have taken the ferromagnetic moment from chromium, because there is a little canting of chromium moment, not perfectly antiferro, and ytterbium this moment, and by taking the external field and internal field, we are able to reproduce this magnetization reversal. This is another example from the spinel systems, where you see, by the way, this has other interest with regard to lithium battery materials. I will not go into that. And here I like to point out only one observation, that when you do DC magnetization, let us say you see this curve, so-called B, you know, I mean, if one is a little bit casual in the sense you see magnetization, and if like in textbook, if you see very old textbook, you will see this kind of so-called magnetic compensation. But if one is not very careful, one will be missing this fine structure, what is shown here. In fact, it passed through two zeros, you know. So you see each and every curve passes through two zeros. So, and not only that, how you do the measurement, field cool warming or field cool cooling. This is a shift. And here I have summarized that compensation temperature as a function of external magnetic field. This one compensation temperature, which is here, that does not change with field. And that is also constant whether you do measurement in field cool cooling or field cool warming. So this particular one. But the other one, what is it changes the side, you know, whether it is field cool warming cycle or field cool cooling cycle, and that is also field dependent, but at relatively higher field, typically 500 oersted, where the magnetic field is able to, the Zeeman energy is able to suppress or overcome the internal anisotropy, then these two also merge, all three merge. In fact, so all four merge. So this kind of fine observation is possible by doing very careful studies, but that's why I'm saying one has to be very careful when one does the measurement to understand this kind of complex magnetic behavior. Another system which we again work with for Deepak, Professor Suresh is attending. In fact, he is one of the doctoral committee members of this student. And so here, what you see, magnetization as a function of temperature, and you see how this magnetization negative, but at higher field, not very high, it becomes positive. So this kind of reversal is possible even with small applied field. So here there are two things: temperature dependent magnetization reversal, as well as field induced magnetization polarity reversal. Both are, you see. But one point I would like to address, bring to your attention here, that exchange bias, you see, as a function of temperature, of course, here we use 1 Tesla cooling field. Exchange bias occurs at the compensation temperature and picks up and then goes like this. So this is another correlation between the negative magnetization and exchange bias, which we have established. This is the example on the garnets. And what you see, garnet, what is the difference in garnet? Because garnet is something where you have three magnetic sublattices, as you know: octahedral side, tetrahedral side, and dodecahedral side. By doing neutron diffraction, and as you see, the growth of magnetic peaks, and also the addition of magnetic intensity at lower temperatures, we could calculate the magnetic moment, order magnetic moment, as a function of temperature of each and every individual sublattices, octahedral, tetrahedral, and dodecahedral. And each one we have modeled with the theoretically expected, that is the calculated one. And then this is the net moment of this formula unit, which shows the reversal, and also our calculation, mean field calculation matches perfectly. So this kind of fine understanding is possible with Newton. Now, here is the last example where I would like to point out one important thing. So far, this is what has bothered me many times, that so-called magnetization reversal we have seen with respect to DC magnetization, okay? And whether it is exchange bias, that is also DC based on DC magnetization. Now, can we have some independent way to reveal, some different way of reveal this phenomenon? Of course, you could see one, the dielectric constant, which has typical features across the compression temperature. But in this material, which is a intermetallic alloy, we'll be showing the magnetoresistance. So we'll be showing that magnetoresistance also changes sign, and also it passes through zero compensation. So this is another independent study in terms of probe, how it looks at the magnetic system. That is what I am trying to tell you. And this is but what happened? Those oxide materials, in fact, in my lab, we tried to measure magnetoresistance of those either ferrites or perovskites, but resistance is so high that it went out of our measuring limit. But here we could do it, and this is the crystal structure. Here again we show that magnetization is changing sign, and we also show the field dependent. Very nicely we reproduce. This is not yet published. This is also again Deepak's work, my students' work. So magnetization changes sign with the field. And this is a Neutron depolarization study. Again, it corresponds the reversal of magnetization. This is the compensation temperature, full recovery, and so on. And by doing Neutron diffraction, we could again measure the side moments and the net moment, which shows magnetization reversal. But here is the magnetoresistance data. See the resistivity as a function of temperature at two fields, 0 kilostate and 70 kilostate. We see the crossover, And when you plot the magnetoresistance of this material, then you see magnetoresistance also passes through the zero. So this is I being practitioner of this subtopic of magnetization of magnetic phenomenon. I was really looking for this kind of evidence over these years, and first time we could show that indeed there is resistivity. It measures different principle, and we could establish the polarity reversal of magnetoresistance, which is again linked to magnetic phenomenon. And so this is very important observation I wanted to bring to your attention. So with this, let me summarize that today, in this limited time, what I wanted to speak about the novel magnetic phenomenon called magnetization reversal phenomenon. If you see our review article, so by now we have studied a lot of other systems. We have gone more towards establishing this phenomenon with regard to cross correlation with other physical properties and more deeper understanding and independent way of establishing this phenomenon, not only from DC magnetization point of view or exchange bias point of view, but if you see this kind of, if there is a negative exchange coupling among two ferromagnetic sublattices or ferromagnetic or canted antiferromagnetic sublattices or ferromagnetic, canted antiferromagnetic or paramagnetic sublattices, then you would expect imbalance of spin and orbital moment can also give this kind of magnetization reversal. Interfacial exchange coupling between ferromagnetic and antiferromagnetic phases also can give, which so far we have studied all bulk material, and in one case, nanoparticle case, I showed you that the interface is formed due to core and the surface disorder, the interface that gives. But now we are going in real 2D thin film multilayer material by creating interface in this material, and we are now working in this direction. So in all these cases, the exchange bias, magnetization reversal is expected. And as I said, when magnetization changes sign, here we have shown as a function of temperature, we too feel that it goes from negative side to positive side. So basically magnetization state goes from 0 and 1. So magnetic bistable system. So this is very good for practical application in magnetic memory. And the last slide where I tell you that when this can be used for thermally assisted magnetic random access memory. You all know that this is the antiferromagnetic layer, which is exchange coupled with this ferromagnetic. This is another antiferromagnetic exchange couple, but this is more rigidly exchange coupled. So this is this serves as the reference layer, and this is the storage layer. Where the storage layer magnetization is antiparallel or parallel, that gives two states. Now this is done by applying DC magnetic field to reverse it. Okay, for that one has to break this exchange coupling. Okay, but in our case, as you could see, by varying temperature, one can get the magnetization reversal. That means if you pass DC current, there will be Joule heating, and Joule heating is cause the temperature to change across the compensation. The magnetization will flip, and you will get the other state. So above compensation one state, below compensation another state. So this will be much easier from practical application point of view, because you don't have to apply DC field, just resistive heating will do the job. So this is what we have proposed. With this, let me acknowledge the contribution of my colleagues and students, Amit Kumar and Madhu Ghanate. She completed PhD with me under Isbana, and Deepak, who is about to complete his PhD. With this, I thank all of you for kind attention. Thank you so much.
Thank you so much, Professor Yusuf. It was a very exciting talk. Now I open the floor for a few questions from audience. Anyone in the audience have questions? Yeah, Professor Santosh has raised hand. Santosh, please go ahead. Yeah.
I have gone through the review article, and it's a pretty detailed article. I have a question. If there is a system which doesn't have a long range magnetic ordering, and it's looks more like a glassy phase, And if that shows a negative magnetization, how do you, is there a way to kind of decipher that?
Yeah. See, as I very briefly touched upon one of the nanoparticle system, chromate nanoparticle, see the surface disorder that is also glassy phase. So essentially what you need to have at the atomic scale, that kind of interface between two magnetic sublattice equivalent. Okay. So whether it is glassy, say when it is glassy, you can have the net some under magnetic field. See, DC magnetization is always done under magnetic field. So you can have some net moment out of the glassy phase under DC field, and other sublattice, which is, let us say, antiferro. So this kind of two sublattice, if you can imagine, you will get this effect. But you have to remember that you are doing this measurement under field, so-called glassy system also has a net moment. Okay, so that is the way you can explain. Hello.
Yeah. Thank
you. Any other questions? Audience? Okay, if there are no more questions, I will ask one question.
Yes.
Professor Yusuf, actually, I am really thrilled to see this effect in many systems, including the system where you have single magnetic sublattice. Yeah. You have touched upon this imbalance of S and L moments. Do we have an example system?
Yeah, this good point. So this I took because Professor Grover, Arun Grover, when he was in TIFR, in fact, they showed in one example that in a radar system, spin and orbital, imbalance can give it, but it is there. So we have not, I have not worked on this part yet. Okay, spin and orbital.
Okay.
Thank you for raising the point. In
Thank
fact,
you.
I had lots of discussion with Professor Grover in this regard.
Okay. One more question. In this cobalt chromium iron oxide system, you have shown neutron depolarization experiments.
Right.
So below the compensation point, your depolarization signal again grows.
Right.
Does it mean that this mesoscopic grains, which have got zero moment, again moment starts growing?
Yes. See, as you see in DC magnetization, what you see that above compensation you have magnetization, below compensation also you have magnetization.
Yeah.
So that means above and below both cases domains do have magnetization. Okay. Only question is either it is in one case it is aligned along the external field direction. Another case it is aligned opposite to the external field direction. So domains do have magnetization both above and below the compensation, and that is what is getting reflected in neutron depolarization study. That's why below compensation you again see depolarization.
Okay. Thank you so much, sir. Thanks again on behalf of the organizers for this very exciting talk. I hope we will hear you again in another such meeting. Thank you.
Thank you.
Yeah, thanks. So next we have Professor P.N. Santosh. So can you kindly unshare your slide? Yeah, thank you. So I am happy to introduce Professor Santosh. He is a colleague of mine, a full professor at the Department of Physics, IIT Madras. Professor Santosh has completed his PhD from the NCL Pune, and he has gone on to do a postdoctoral term at IIC Bangalore and then Ohio State University. And he also spent quite some time at the Oxford University before joining IITM. And he recently served a visiting scientist position at the Kyoto University. And also, as you know, he is our most recent MRSI medal winner. 2021 prize went to him. So Professor Santosh is well known for his work on structure property relationships on complex oxides. He works on very many oxides, starting from simple perovskites to very complex systems. And his today's talk is also going to dwell on one such complex oxide system where he sees giant exchange bias. In fact, in some sense, this is going to be also a sequel to the previous discussion we had, because you also have competing magnetic interactions again. Professor Santosh, please.
Thank you, Nirmala. Hope you can hear me loud and clear.
Yeah, perfect.
Right. Good morning, all. The title I am given here is Competing Magnetic Interactions in the Exchange bias behavior in complex oxide materials. Okay. I'm thankful to the organizers for giving me this opportunity to give the invited lecture here. This is a college which I used to regularly hear a lot about from Anil when we were doing PhD together. So I think at least 3 of my friends are have graduated from this college. So it would have been better if we had the chance to kind of visit this place and give a lecture, right? Hopefully in future. So let me start by giving this lecture on this exchange bias behavior in some of these complex materials. This is a theme which I have been working on for the last 3-4 years. So I have organized the talk, give a very brief introduction on perovskites, a Rudolfson proper structure and hexagonal perovskite, what are they? And then I will go a little bit detailed on the magnetic and exchange studies on this Rudolfson proper system, strontium, lanthanum, cobalt, manganese oxide. And thereafter, I will touch upon the hexagonal system. But how much I can touch upon that depends on the time, right? Now, what are these perovskite systems? I mean, these are written generally as ABO3 system, and tons of studies have been carried out on these particular system with various compositions. So how do we generally, people researching on these materials, I mean, kind of engineer or decide on the materials? There are, I mean, roughly a couple of ways. I mean, this increasing the chemical pressure. For example, barium titanite is a well-known example, which all the students obviously know from the textbook. It's a ferroelectric material. Now, the barium sits at the center of the cube, and the titanium sits at the corners, and the oxygens form the octahedra around the titanium. Now, if you change the barium to a slightly smaller ion like strontium, there is a change in the bond distances. So that have an effect on the properties. And when you go to still smaller cation, so you are basically changing the internal chemical pressure, then the octahedra stills, and then it have a different dielectric property. So, for example, calcium titanate has a paraelectric state, strontium titanate is an incipient ferroelectric, and barium titanate is a ferroelectric state. So incipient ferroelectric means if you apply a little bit of pressure, it goes into a ferroelectric state. So the sizes varies from, so the calcium is around 1.16 angstrom and barium is 1.31. So you're talking about 0.15 angstroms of total change, and it has changed the physical properties completely. The other way to do is the titanium here has no d electron, no electron in this d orbital. So it's a d0 system. Now you start filling the d orbital, then you start seeing magnetic properties. Like, for example, if you have a d1, d2, in these particular systems, strontium molybdate or strontium mandate, you get paramagnetic conductors. And if you fill in more electrons, you will get into ferromagnetic conductors. Furthermore, you get into antiferromagnetic insulators. So you can change the chemical pressure or the d electron count to achieve a large range of properties. That's pretty much what we generally do. And if you manage to put two different ions in the B side, instead of titanium, or instead of titanium here, you put two different ions, iron and molybdenum, then you get this exotic system like half metal ferrimagnet. And in this particular system, iron and molybdenum octahedras are shown in purple and oxygen yellow colors, but they are ordered. Every ion has molybdenum as the neighbor. So depending on the extent of ordering, the properties can change. I actually usually give this particular, this is a transparency of Professor Woodward, who was my postdoctoral advisor. He regularly uses to introduce the subject area. So this has been done, and quite a lot of work presented by Professor Yusuf today has been on this perovskite system. And then he also touched upon spinel structures, but a lot of perovskite he actually touched upon, and he still works a lot on that. So what we have done is make the system layered. For example, this is a perovskite building block, and then you start filling in, putting in another AO layer, which is a strontium oxide layer or a lanthanum oxide layer. So this is a perovskite building block. These are the perovskite building blocks. You introduce something like this, so that goes in between these perovskite blocks, or you can see better in this. So these are the perovskite block, and then you incorporate the AO. You can see that there is a gap which forms. So in essence, what you see is you increase the distance between the perovskite blocks, thereby reducing the interaction along the C-axis. So the magnetism or the electrical properties are, more confined. It's not completely confined, but more predominant in the x-axis, XY plane, rather than along the C-axis. So in some sense, you have gone into a pseudo 2D system. So this has been studied. The well-known superconductor came from this structure. There are enough studies on multiferroic systems and electrochemical properties, colossal man torusins. A wide range of physical properties already have been reported in these systems. Okay. The other structure I talked about is a hexagonal structure. I will not go much into this, but I just this marked one called 6H perovskite. You can see, it's a slightly, all these structures, you can see this, this dimer, which is two phase sharing octahedra, connected to the next layer through this corner shared octahedra is the kind of structure you get. So essentially you have in the phase sharing octahedra almost like a direct metal to metal interaction. So that makes a magnetic interaction more interesting. So there is a lot of interest in this 6H perovskite recently because of the observation of quantum spin liquid behavior and novel quantum phenomenon in the 6H because of its triangular lattice kind of a formation. So I will not go into that part of it. Predominantly the exchange interactions we are talking about, which decide the magnetic properties in these systems, are called the super exchange interactions. So for example, if you have two manganese-free ions talking to each other through an oxygen ion, so it forms a semi-covalent bond where the electrons shared in the bond. So there are certain rules put up by Goodenough-Kanamori Anderson rules, which kind of tells you whether something is ferromagnetic or antiferromagnetic, etc. Antiferromagnetism is predominant, but there are enough examples in the literature where you can have weak ferromagnetism also. I'm not going to talk about the DM interaction, which is not very important. So what we have done, or the first part of the work, is the Rudolfson-Popper structure. We have taken the classic system of La2COMnO6, which is a ferromagnetic insulator. And it is well known ferromagnetic insulator. It has its magnetodielectric property, but it has a ferromagnetic transition around 150 K. Okay. Now, what happens if you make it layered? So essentially, you introduce a strontium oxygen layer in between the perovskite blocks. Perovskite block is the ferromagnetic layer, and you increase the distance between the ferromagnetic blocks by incorporating a strontium oxide layer. So if you do that, you are weakening the magnetic interaction along the z-axis, and what do you get? Okay, so I will take this as a parent compound and want to see what happens to the magnetism if you reduce the interaction along the z-axis, but the XY plane interactions remain intact. Okay, I'm not going to the whatever is written on the left-hand side. I'll keep to the right-hand side of the picture. So I will ask you to concentrate on that. Okay, so we are able to make this system. So this is a perovskite building block, and then you have introduced the strontium oxide layer. So you essentially have increasing distance between the perovskite block. Actually, the perovskite blocks are also shifted halfway across the diagonal in the structure, but that's not important. But we are just saying that we are increasing the distance between the perovskite layers. So what we do, we need to make sure that the system is completely formed in the single phase. That we do by an X-ray diffraction followed by a ritual analysis. And we are pretty comfortable saying that it's a very good single phase system. Okay. Now, in the parent compound La2CM6, so this has a manganese 4+ and cobalt 2+ interaction, which gives them the ferromagnetism. So we want to see whether that ionic state remains the same in our layered system also. What we see is by doing an X-ray photoelectron spectroscopy, you have both, cobalt and manganese in a kind of a mixed valence state, and we get that cobalt 3+ and the presence of cobalt 2+ and manganese 3+ and manganese 4+, and predominantly it is cobalt 3+ manganese 3+, and the ratio is as given here. It's more of cobalt 3+ and manganese 3+. But there is a presence of manganese 4+. It's not a small amount, but it's a fairly significant amount. So you have a presence of significant mixed valency in the system. Okay. Now we look at the magnetism. So you see around 150 K, we get an upturn in the field called magnetization as well, and is at FC. Which is the parent ferromagnetism somehow is still present there, but it's not as strong as that. But you see at the lower temperature at 50 Kelvin, there is another feature. So what is this feature about? And then we do the conventionally we look at the paramagnetic region and see do a Curie-Weiss fit to understand what is the spin state of the magnetic metal ions. And so these are the fit parameters of theta p of 98K, which shows that there are ferromagnetic correlations. A positive theta p here gives you that there are ferromagnetic correlations in the system, and the mu effective is found out to be 4.86 mu b per function unit. Okay. The hysteresis loop shows at very low temperature, there's a large hysteresis. At room temperature is like a paramagnet, what you expect here. But at very low temperature here, you could see a hysteresis loop, showing there's a bit of ferromagnetism involved. Okay. And these two transitions also can be seen by the first derivative of the curve. You see these peaks corresponding to the two transitions. One we call it a ferromagnetic, other something else. We don't know what it is. So how do we kind of look at it? So we go to the one way to do is, as you have seen Professor Yusuf talking about, is using a neutron diffraction, which is a pretty common tool he uses, but we get to use once in a while in a important system we managed to do it. So what we find is, I mean, I just put the data at different temperatures to show that they're pretty identical. There are no extra peaks. So if you have an antiferromagnet, you will see an additional peak sometime. But you have a strong ferromagnetic system, you will get see increase in the intensity at lower temperatures. But our analysis of these things shows that there is no presence of a long-range magnetic order, neither ferromagnetism nor antiferromagnetism, which is long-range order. So that's the essence of idea we get from the neutron diffraction data, right? Now, when you have a system which have the presence of ferromagnet and antiferromagnet, you can end up with a glassy phase due to frustration, etc. So the competition between ferromagnetic and antiferromagnetic interactions and characteristic features, spin glows or slow relaxation and magnetic memory effects. So we can expect to have something like that when you have a competition. So our system, Neutron says there's no long-range ferromagnetic ordering, nor there is a long-range antiferromagnetic ordering. But in the magnetization data, M versus T, you see a signature of some ferromagnetism. The Curie-Weiss fit also suggests that. And considering the fact that you have a mixed valency, the presence of cobalt 2 plus cobalt 3 plus, manganese 3 plus manganese 4 plus, it says, I mean, there can be interaction between each of these, or between manganese cobalt 3, manganese 3 plus cobalt 3 plus manganese 4 plus cobalt 3 plus, etc. So there could be a fairly large complex interaction between these ions, which can lead to a glassy characteristic, right? So when you have a glassy characteristic, magnetic glassy system, you also see some memory effects. Essentially, the system have, as I said, there are several local energy minima which each can freeze upon, and so we can have memory effect corresponding to that. So what we do is take the magnetization curve in a zero field cooled, cool it all the way down, and use that as a reference curve, and take the warm-up curve, and then you have a cooling down where you at some temperature you have a waiting period. So you, for 3 hours, you keep the system cooling at kept at a particular temperature. Here we have taken at 40 Kelvin, and then cool it down, and then you warm it up, take the again. So difference between the two warming up curve shows there is a dip at the temperature we kept it for, we halted the system. So that says that the system remembers where it was halted. So you can do the similar thing with a field cool protocol where you do the same process in the presence of a field. So wherever you have kept the system halted, you see these signatures of where the system remembers. But you do, we are also done at higher temperature. So these were done at low temperature where you see in the magnetization curve, we have a second transition. So at a higher temperature, where a ferromagnet is involved, we do the same thing. We don't see any memory effect. So it's seen only at very low temperature. So the glassy phase exists at very low temperature. The other way to significantly look at AC is by doing an AC magnetic susceptibility. So you have two peaks here, one at 150 K corresponding to what we call at a ferromagnetic system. The other one is at high at the lowest temperature. So the high temperature 150 K with different frequency, the peak doesn't shift, which shows it's not a glassy transition, but the low temperature transition actually shifts. And we can analyze this curve due to using a critical slow dynamics model or the Vogel-Fulcher model, and looking at the Midosh parameter, which looks at the peak shift with respect to the frequency. All those parameters basically tells you have a interacting magnetic glass, or what you call the clustered glass system. Okay. So now, briefly, I mean, the idea was exchange bias. So if you have an interface between an antiferromagnet and a ferromagnet, and then you cool it down, you will see a shift in the peak, which you call it the exchange bias. So the ideal, the condition should be the Tn should be less than the Tc. The ferromagnetism should happen initially. And then it can have an exchange bias because of the pinning effect at the interface between ferromagnetic and the antiferromagnet. So we have a system where we have a competition between ferromagnetism and antiferromagnetism, but not long range, but you have several nanoscale domains where you have these interfaces formed. So will that show the exchange bias phenomenon? So that's what we investigated, and we see a fairly large exchange bias, something to the tune of more than 5 kilohertz, probably the largest at that stage reported on a layered oxide. And you can see that the exchange bias with respect to temperature, it exists below only the glassy transition of 40 Kelvin. Above that, there is no exchange bias. And depending on the cooling field, it have at higher cooling field, it kind of saturates. It's a pretty well known. And we also, to confirm it's not an artifact, we have done both positive and negative cooling fields, and the exchange bias shift to the opposite sides, which confirms it's a real system. Okay. We can also, do what you call the training effect study. So where you cool down to the lowest temperature, do a hysteresis loop, you see the exchange bias, but you keep looping many cycles, and then the exchange bias keeps reducing. That's because in a system like this, there is an interface between ferromagnetic and the antiferromagnetic region, but that antiferromagnetic region kind of at every cycle kind of rotates and things like that. So there is a change at the interface, especially at the antiferromagnetic side. So that can lead to this training effect. We can fit this by a particular curve by Mishra et al., which takes into consideration the presence of both rotating spin as well as the frozen spin. So that can actually fit our curve perfectly, and then we find that this is correct. Nirmala, how much time do I have?
About 5 more minutes.
Okay. Thank you. So what we have done, so this detail of this work can be seen in the publication by Ranjana, my student, in PRP 2018. And so what we have done is, as a continuation of this, take another system which is called lanthanum strontium. Instead of manganese, you have iron. So if you take this system, the parent compound, the perovskite component, is not actually a ferromagnet, it's more of an antiferromagnet or even glassy. But when we do this, we don't see any exchange bias in there. So you don't see exchange bias in any system. So what we did was, slightly engineer the system and incorporate manganese into that, because we know the manganese cobalt interaction generally ends up giving a bit of ferromagnetism. So we have 2 different compositions where you have either cobalt rich or iron rich compound, and then see what happens to these. So we are able to make single phase of the system. You can also see from the composition that you have 3 different ions. You have a complex magnetism there, because iron manganese can interact, manganese cobalt can interact, iron cobalt can interact. So it's a complex system. So will it show will it form a system which can show a glassy phase and thereby the exchange bias phenomenon? So we see exactly the similar results, whereas when there is around manganese, it doesn't show any exchange bias. It's like more like a paramagnetic system all the way down. And you see exchange bias phenomenon in this which is pretty impressive. And at 2 Kelvin, probably one of the compound system, which is FMC2, which is the cobalt, which is FMC2 is the iron-rich compound, shows a pretty high exchange band of bias of 9 kilo. Okay, so we have done exactly the same sort of analysis, and what we find is, I'll click that. The FMC2 sample have more stronger antiferromagnetic domains because of the presence of more amount of iron. Iron-iron interactions are fairly strong antiferromagnetic systems. So we have a interface between, a large number of antiferromagnetic regions along with clustered glass regions that seems to be driving a larger exchange bias compared to this. But we don't have a local prop to say that this analysis or a pictorial representation is exactly accurate, but we believe that is the case. This also is published as in 2020 in a PRB. So I will briefly explain. I will not go into the detail, but we have briefly taken up the hexagonal system where you have the phase shared dimer, and you have the corner shared octahedra. So here you put a mixed valent of iron cobalt, then do we get exchange bias in these? So this is a bit of study. We see why we got single phase system. We see mixed valence in this system, mixed valence in all the 3 ions. So that makes the system extremely complicated, and we see a hysteresis loop at lower temperature. And these are a simple study to figure out the magnetism. We also do at very low temperature, we think it's a glassy phase, and we have done the memory studies to show that the memory effect exists in this system. We did the neutron, this neutron diffraction was done in ILL, and what it says is there is no long-range magnetic coordinate at the lowest temperature or at any temperature. The statistics of this data is not exactly great, but I think the analysis is fairly good. So this shows also there's a glassy phase involved, and we see similarly exchange bias, but not very high, 3.484 kiloastet, but we see exchange bias. So I'll not go into that. So what we quickly, Nirmala, in a minute, we have done a DFT calculation in the Rudolph system to see whether is it possible to build a model to see the exchange bias is present. So we made this interface along the XY plane, and then that's a cobalt system which is ferromagnetism, and the manganese dominated region which is ferromagnetic, and then you flip the ferromagnetic moments from one direction to other. If there is an energy difference, that means there is a possibility of exchange bias. So what it says is the interface created in the nanodomains, and also confined to an XY plane, that is enough to drive the system to show a large exchange bias. So you can see a wide range of systems as a conclusion which can show exchange bias. The interface phenomenon at the nanoscale domain is sufficient to drive this. But a recent paper by one of the group making a single crystal of simple perovskite to show that the exchange bias is not there, pointing at the fact that the grain boundary effects are very important. But we believe that the grain boundary effects is not alone enough to give exchange bias, because our system of lanthanum, strontium, iron, cobalt doesn't show any exchange bias in a polycrystalline sample. So it's an interesting area. Still a lot to be explored. I think I will stop at that. I'll be happy to answer any questions. Thank you.
Thank you, Professor Santosh. Audience, do you have questions?
Hello, sir.
Yeah, please go ahead.
Sir, which DFT method you are used to compare your study, sir?
I personally don't do DFT. This was done by Professor Ranjit Nanda, and I believe he has used a quantum X processor for doing this calculation.
Okay, sir. Okay. That's because I am also using quantum espresso for DFT calculation. So this magnetic studies, can I do with that software? I just want.
Yes, I believe. I think if you have any specific questions on that, I think Professor Ranjit will be the ideal person because I don't handle that, but it can handle magnetic systems perfectly.
Okay, sir. Thank you.
Any other questions from audience? Okay, I have one question, Santosh. So you mentioned that in the second system, this is this LASR iron cobalt 0.5, 0.504. You do not see any exchange bias.
We don't see any.
Right. But you do have two sublattices, both iron O iron and cobalt O cobalt.
What we find is like, in a double perovskite, maybe iron cobalt orders at least partially, but in our diffraction studies, both our first system and this system, they are randomly ordered. So I don't know whether I can call it two different sublattices. Probably you can. Yeah.
Okay.
It's a severely disordered system, so you would expect a competing magnetic interaction.
Yeah. But then you do not see exchange bias, right? That is very interesting.
We don't see an exchange bias. So that's why we didn't do too much of try to do a bit of neutron or anything on that, because I mean, you essentially have to make at least 5 grams of samples. And we did the initial magnetic measurement. That was disappointing. So Nirmala, you might be aware of, you know very well about Pratish's work. And lanthanum, strontium, and cobalt. One of them, I think one of them at least shows some sort of ferromagnetism. So the idea essentially came from that. But we don't see an exchange bias. So we didn't pursue it further, but rather we modify. Because many of the systems, if you have a manganese cobalt contribution combination, you end up getting a bit of ferromagnetic interaction in that. So we just played around with 2 compositions. Ideally, you should be able to do more composition, but then it's a messy system. So.
Very interesting. Thank you. So any other questions to Professor Santosh? Okay, if not, let us thank him. Thank you, Santosh. Thanks also from the organizing committee. Yeah. Now we will move on to the next presentation, and let us invite Professor K.G. Suresh, who is a senior professor now at Department of Physics, IIT Bombay. Professor K.G. Suresh has shown consistent excellence from his undergraduate days. He graduated both his bachelor's and master's degrees from University of Kerala with a medal, and his PhD in physics is from physics department, IIT Madras, my alma mater too. So I always look up to him as my big brother. So as I mentioned, he continued to excel both in research and teaching. He has won the MRSI 2020 medal, and he's also DAE Young Scientist Project Award winner. And recently, he has also received the Excellence in Teaching Award from IIT Bombay, and also the LEAP Award 2020. And the latest is he is now elected as a chair professor, IIT Bombay 2022. Congratulations, Professor Suresh. And he has many publications spread over varieties of magnetic materials. Particularly, he focuses on spintonic materials, magnetocalorics, and Huesler alloys, and topological systems. In today's talk, he is going to focus upon Husler alloys. He and his group have worked very extensively on many different Husler systems. I am sure we are going to hear a very good summary of those findings. Welcome, Professor Suresh.
Thank you. My slide is visible?
Thanks. Yeah, it's visible.
And I'm audible?
Yeah, you're very much audible. Thank you. Yeah.
So first of all, let me congratulate the organizing team. I know Sunil and Bhagya. They have done a very nice organization. It's going on very well. Several communications have been receiving. Very nicely organized. So congratulations again. So thank you, Professor Nirmala. Again, nice to be in a session with you. So I will give you, as you rightly mentioned, I will try to give you a summary because this is a topic which I thought I will introduce. Therefore, I will not be able to go into the details. I will give you the salient features of this class of materials, like the perovskites, which Professor Santosh gave a very in-depth study. So similar things exist for this alloy system, this material system also. Of course, this is an alloy system. So I thought I will give you an overview, highlighting some of the important aspects which are yet to be understood or which are very promising, both from the point of view of fundamental physics and also from applications. Not only from the point of view of condensed matter physics, some of these excitements are appealing from other topics of physics as well. So therefore, it is important that we have some idea about what is going on in this alloy system. And therefore, my talk will essentially cover those aspects. I'm sorry that last 2 years, because of COVID, we don't have too much of new data. And therefore, some of the results or many of the results that I'm actually going to show, some of you would have already heard, but I think you will excuse me. But of course, some of the things are new. So let me begin with this thing. So I'm going to talk about only magnetic aspects of these Husler alloys, but these alloys are known to have other things also, but I will not talk about those things today. So the plan of my talk is something like this. I will give you a very brief introduction about these Huslers and then the role of these alloys. I will just touch upon that. And mainly I will talk about the importance of this one in the context of the results that our group has obtained recently. And I will also talk about some of the future perspectives. So just to give you this, what is a Husler system? This is basically an alloy. The alloy consisting of only transition metals mainly. And usually they are represented by this formula unit X2YZ, where X is something like what is shown here, almost the transition metals, and Y is something like this, and then Z is here. Of course, it's also true that the Y can be from this rare earth family. At least these are known to form. The problem also lies here. So what is the problem? The problem is that if you see X and Y, I mean, in fact, X, Y, and Z, they are all kind of neighbors, and therefore anti-side disorders are very easily likely to happen. And therefore, this is actually an issue which one has to keep in mind, because we are actually mixing three elements which are not very far away from the periodic table in most of the cases. And therefore, this can actually result in many times unwanted disorder that actually can be very bad many times, and sometimes actually it can be helpful also. So broadly, they are classified as a full, that is X2YZ, and the half Husler, they are represented by XYZ. So basically, we start with the full Husler that it can be thought of as a 4 FCC sublattices, interpenetrating FCC sublattices, and the different atoms corresponding to this ABC shown here are can be represented. ABCD can be shown here in this with these atomic positions. So what happens is, as you can see, there are various possibilities here. One is, of course, this X2YZ, which is also called the 211. So if usually what happens is one of the things is occupied by Z, one of the 4 things. So the remaining 3 can be either by X or Y. As I mentioned, X and Y are very close to each other in most of the properties, electronegativity, size, and so on. So all of them are occupied by the same atom, then it becomes what is known as a DO3. So DO3 will be a disorder in that sense if it actually is forming like that. Then other possibilities are you have what exactly as mentioned is a full Husler system. It can be X2YZ or it can be XY2Z also. So one is called that, this is called the normal and this is called the inverse. They have different properties because magnetism is going to be very different between these two. Then this very interesting thing, which of course our group has been very much focusing, is what happens is when you have something like x prime y z, what happens is that the first one, instead of x2, you have two different x elements from the group which I mentioned. So this is called, so this is basically 1-1-1-1 composition. It's also called equiatomic Husserl alloy, or it's also called a quaternary. So then the other thing is that, as I mentioned, suppose one of the x is vacant, then it becomes the half Husserl. It is the XYZ formula unit. Why are they important? They are important due to various reasons. In fact, like the perovskite family, it has got many functionalities. They are truly multifunctional. So some of the things I have shown here, which I am going to present, at least touch upon today, that is this one. They are well known for the magnetocaloric materials. They are very well known. In fact, before that actually is a magnetic shape memory effect. Then many fundamental issues like a heavy fermion systems, Kondo systems, superconductivity, all these things are there in some of the systems. Then of course, they are also in sought after things for the rare earth free permanent magnets and so on. But I will talk about, I will mainly talk about the spintonic aspects of this. I will talk about some kind of antiferromagnetism or ferrimagnetism. I will also talk about different types of semiconductors one can get, mainly the magnetic part of that is magnetic semiconductors. It's also true that they are going to be very promising from the point of view of topological materials. That is, these are the things which I will touch upon today with a very brief introduction. I will not go into the details at all because of the time constraint. I will just touch upon. So when we talk about the Husserl systems, especially the equiatomic systems, which I am going to focus, the main thing is with respect to the spintonics applications. So basically, we should have some idea about what kind of things we are talking about. As you know, that in magnetic recording industry, which is magnetic recording is one of the most important applications of magnetic materials. So when we look for these newer and newer materials, the idea is to have a much better recording density. When you increase the recording density, of course, there are problems also with respect to, so recording is one thing, but when you have to get this data read, there will be problems if you actually exceed these recording densities beyond a point. So, but still there are techniques or developments in that aspects also. Therefore, what is going on continuously is that to reduce the size or reduce the number of spins which actually can store the data without much of a problem. So this is the effect, which I mean the effort which is always going on, and it will continue. So the point is whether you will be able to get newer and newer materials with where the number of spins will be reduced, the size is reduced, that is equal to saying that the number of spins is reduced, where you will be able to record with a larger or higher and higher recording densities. Some of the numbers are written here. It will be useful if you want really looking at it, and also some length scales are also very important. I will not go into the details of it, but basically what you are trying to do is that you are trying to get newer and newer materials where the recording densities can be better and better. At the same time, you will be able to have very little noise problem as far as reading is concerned. Otherwise, it doesn't make sense. If you just record it with very low, great density, but if you are not able to read it, then of course it doesn't work. So in that aspect, the most important thing that one has to worry about is what is known as a half metallic ferromagnet, because as we are going to see, these half metallic ferromagnets, you have a spin polarized band structure where you have one type of spin which is behaving like metallic, like you can see that Fermi level is within the band here, whereas there is a gap corresponding to the other spin, that is a spin down or the minority spin state at the Fermi level. Therefore, you are guaranteed that at the Fermi level, where the conduction electrons are, the electrons which are very close to the Fermi level, only those actually contribute to any kind of conduction or any such physical response. In that respect, you see that only in this particular band structure, you will see that only one type of spin will be contributing, or this is essentially giving rise to what is known as 100% spin polarized current. You are not talking in terms of the electrons, but you are talking about spin up currents in this case. So this is an atomic picture which give you some idea about how you can actually get this kind of a spin polarized band structure. Obviously, it depends on what kind of an overlap you have among the three, among the atoms, which are in this case Ni, Mn, Sn, which is Sb, which is the prototype half metallic ferromagnet, which was discovered long back, and which has actually stimulated a lot of interest in this field itself, and that is what is going on today. So basically the idea is that to identify or get materials of this, where the band structure is of this kind. Another very important material, it's an oxide material, which was known again some long back as far as the half metallic ferromagnets are concerned, is this one, which is chromium oxide, one of the oxides of chromium, where you can see that very clearly there is a gap at the Fermi level for the downspin band. So it's practical material, room temperature, 100% spin polarized material, which has been in used for some of the applications. It is known for a long time. So this is a very standard material today because it was one of the early days of discovery of this field. So if you have such materials, you are guaranteed to get what is known as a pure spin current. So what is shown here is a charge and spin current, but that actually has the usual problems of losses because the current is actually moving, charge is actually moving. So this is a case where you have only one type of spin is moving. So there is again a charge movement, therefore there will be a current. So there will be, there will be a charge current also, and that will give rise to some electrical resistivity. Whereas if you have this kind of a situation, one can actually mimic this kind of a situation where you have one type of spin moving in one direction, other type of spin moving in the opposite direction. How to get it? Suppose you have a very strong spin momentum coupling, then this is guaranteed because spin and the direction of motion are coupled because of the very strong spin momentum coupling, and then you are guaranteed to have this kind of thing. So there will be no net effect, there is no scattering of these forward moving electrons to the backward side, and therefore you will be having almost a resistance less transfer of spin from one to the other, and that actually results in what is known as a spin current. So this is a pure spin current, whereas this is not a pure spin current. Even this is charge current, it's not a pure spin current. So this is the only thing which actually is a pure spin current. So efforts are on. I don't work in those device level things, but basically people are trying to create or generate this kind of a pure spin current. That will be the ultimate goal in any of these applications. They have several advantages, as I've written here. Recording density is one of them, but there are other things, as I mentioned, very low energy loss and so on. So what happens is that what we have done is that we have actually in the band structure, we have added another degree of freedom, namely the spin. So what is going to be seen is that if you add the spin degree of freedom, the materials that we know, they actually get a very different thing that is called a spin analog. I have written as a spin analog. So for example, we know that the magnetic metallic ferromagnets are there. Of course, insulating materials also there, many of the perovskites, for example. But when you include the spin and take the spin into serious consideration, of course, when you talk about magnetism, you definitely take into account the spin. But now we are actually, even in the transport and other things, we actually explicitly take the spin into account. Then it gives rise to half metallic ferromagnets. Similarly, you have semiconductors. So semiconductors, if you add the spin explicitly, then what happens is that you can have either a magnetic semiconductor, I will come to that, or you can also have what is known as a bipolar magnetic semiconductor, which abbreviate as MS and BMS. You can have, you know, some of the semiconductors, conventional semiconductors are gapless, and you can have here a spin gapless semiconductor. We know there are very few semi-metals, but you can have a spin version of that is called a spin semi-metal. And this, in fact, the list, I am not concluding it here because I don't know what are going to happen, what is in store, and therefore this list can actually go on. So as far as the physical properties are concerned, again, there also the spin can actually play a very important role, and spin can make a very big difference. For example, as I mentioned, we talk about charge current, now you talk about spin current. We know that we have this Hall effect, which is very important. You talk about spin Hall effect when you take into account the spin also. We know there are several thermoelectric effects, for example, Seebeck, Peltier, Nernst, and so on. In all these cases, you have a spin version of that, some very exciting field that is today going on. We have very little work, some data we have, but we are not, I'm not showing it today. So a spin version of these thermoelectric effects, there are many. For example, any of these other, most of these mechanisms or properties that we know, in the normal conventional sense, they are all getting into a spin version because of this addition of spin. So both in terms of materials as well as the physical properties, the spin is actually going to make a very different scenario. So let me come to the Hysteresis systems. Why? Basically, in this talk, I am going to concentrate on the spintonic and topological aspects of this. The question is, why Hysteresis? There are several reasons. One of the reasons is that many of these materials can have very high QED temperature. From the application point of view, that is the requirement, definitely. And also because, as you can see, that the tunability is very large in the sense that it can be easily changed from, you can get a series of compounds, you can manipulate the composition, and therefore you can get different properties. But the problem is that, as I mentioned, the disorder is an issue which can actually kill the advantages of the tunability. That has to be kept in mind. This is very important, especially if you go from bulk to thin film and so on, you can have serious compositional issues which one has to really worry about. So what is the history of these spintonic materials in general? It started with, if you remember, I'm sure all of you have heard about this dilute magnetic semiconductors known for almost 2 decades, more than 2 decades. Then came the half metallic ferromagnets. Then came the spin gapless semiconductors, which is again a very important class of spintonic materials today. Then recently, maybe last 5-6 years, people are more concentrating on this antiferromagnetic or compensated or nearly compensated ferrimagnets for obvious reasons. I'll come to that. Then spin semi-metals also. And very recently, people are talking about how people have actually seen many of these topological aspects, both in the normal K-space, which is the usual topology that we talk about, the topology in the K-space, but also in the real space, people are getting the topological features in the form of magnetic fermions. So let me just give you some of the results that we get. Usually, we have been using these experimental techniques. Obviously, I don't have to explain. These are very essential, bare minimum things which one has to do. I will highlight the transport, which is a very, very important to, especially a Hall, which is very crucial in identifying some of these properties of these materials, especially from the topological and the spintonic aspects. Magnetoresistance and Hall are very important. Of course, as Professor Santosh mentioned, neutron diffraction is an expensive technique, whether it is in India or abroad. The amount of sample is large and so on. When it comes to spintonic materials, one of the most important points to be, or the data to be obtained is a degree of spin polarization or the percentage of spin polarization, which can be obtained with the help of this very interesting quantum mechanical effect known as the point contact anti-reflection. And there is a spectroscopic technique, basically it's an IV characteristic in a very different sense, and that actually is giving rise to this information regarding the degree of spin polarization. So this is an extremely useful thing to identify, because all other things you will get some idea about the spin polarized band structure only indirectly. If you want to get a direct estimation of the degree of spin polarization, you need to do the PCAR. It's of course not very easily available in India. Of course, it is true that if you want to get, because the experiments are very limited, the direct evidences are not plenty, unless you have a very good, strong theoretical support. If you combine the two, experimental and theoretical data results, you will not be able to conclude anything. So that is what we have seen. Therefore, theoretical tools are also equally important, I will say. And where we do, of course, with a collaborator and so on, we are trying to do the spin polarized band structure. We simulate the spin polarized band structure and try to see what happens in the experiment. Then, of course, there are various crystal configurations for a given system. In this case, I did not go into the details of this crystal configurations, the ground state, and so on. What are the different non-degenerate configurations possible, and so on. So one has to identify what is actually experimentally. Of course, we know from the XRD and so on, but from the theoretical point of view, also we can generate the crystal configuration for the ground state. Ground magnetic moments, of course. Electrical resistivity is not that simple using a DFT kind of thing, because you have temperature effects coming there. And very importantly, for topological and spintonic aspects, berry phase effects are very, very, very significant. This is a very hot topic today. People have to really calculate. It's a very expensive calculation. One does it, and then you try to compare with, for example, anomalous Hall effect and so on. Then only you will be able to get some idea about the band structure, which is very, very crucial to get an insight into the material. So I'll just take a few systems one by one in the journey that we have been undertaking for the last 7-8 years. So I will just give you one example each in these different classes of materials which I mentioned. So to begin with, of course, the half metallic ferromagnets. So as this is the schematic band structure, as I told you, this is a metallic part. So spin-up electrons are forming a metallic-like band. There is no band gap, whereas here there is a band gap corresponding to this one. So this is the half metallic ferromagnetic density of states, N up and N down. This is the split band because of the exchange splitting. That is what you see. So what is to be done? Of course, you can do a DFT calculation. It will tell you whether there is a gap. Of course, DFT alone cannot be relied upon. You need to have some kind of experimental proof. Experimental proof in the form of an indirect method can come from, for example, the temperature dependence of electrical resistivity. You know that there are different contributions, and different contributions have different temperature dependencies. And by careful analysis of the data or the fitting of these different temperature regimes, you can identify whether there are contributions which can give you information about the the spin polarized aspects. For example, if you know that there are usually the collective excitations called the Magnon excitations at the low temperature for almost all the ferromagnets. So these are known to tell that, okay, because you have excitations, Magnon excitations correspond to spin up and spin down, because you are actually going from a spin up to a spin down ultimately because of this excitation. Therefore, if you are actually getting a Magnonic contribution, that means that you have spin up and spin down electrons close to the Fermi level. Therefore, that cannot be a gap at the Fermi level because they are gapless excitation. So therefore, if there is an absence of this Magnonic contribution represented by, let's say, T square term, which is an indirect evidence telling that, okay, there is no Magnonic contribution. Therefore, you can expect that one of the spin channels is missing, and therefore it has to be a spin polarized band structure. So strictly speaking, one has to really do a direct method. That is what I mentioned. This is a PEC-AR spectrum. The IV characteristic, as I mentioned, what we do is that we take the differential conductance, and from this you can do a fitting. Of course, the fitting is a little complicated, and you can derive the polarization value. In this case, it's something like 70%. I told you that ideally you should get 100%. It's very, very difficult. And only problem with this PEC-AR is that you are actually using a superconducting metal. You are forming a junction between the half metallic, the suspected half metallic material and the superconductor. So therefore, the experiments are limited because of the Curie temperature of the transition temperature of the superconductor, and therefore usually you will be able to get if you are using something like niobium, you will be able to get the data only below something like 3 Kelvin, 4 Kelvin. So that will be the reliable data. So you have only low temperature data. You cannot get a PEC-AR at room temperature under the existing superconducting materials. So that is a severe limitation as far as the PEC-AR data is concerned. So this is one of the systems we studied some time back. You can see that we are combining the indirect evidence experimented, direct experimental evidence, and also the theoretical support. With all these things, we will be able to conclude, make a reasonably sound conclusion regarding the band structure, nature of the band structure, and also the nature of the material system. That, namely, in this case, a half metallic ferromagnet. There are several systems we have done like this, and we could identify many such systems. I just show you only one of the systems. I'll go to another system. Again, I should say that they are all very accidentally happening because we were generally looking at the newer and newer materials from the half metallic point of view. But when we start doing the experiments or the theoretical calculations, we end up in new classes. That is how we actually got into several new classes of materials. So this is which I mentioned as the spin gapless semiconductors, which is abbreviated as SGS. You can see that this spin down band structure is exactly like what I mentioned for the half metallic ferromagnet. But here, instead of having a metallic thing, you have exactly zero gap. So this is corresponding to the gapless semiconductor, but it is spin polarized. Therefore, it is called a spin gapless semiconductors. Otherwise, it's exactly the same. But remember, compared to the half metallic ferromagnets, they are essentially semiconducting because this part is insulating or semiconducting. This is also almost with a zero gap or very close gap when you have some disorder and so on. So basically, this should have a semiconducting property, not like a metallic property. That should get reflected in the transport and so on. So this is what? So this is the conductivity of this particular material. This is one of the first materials that we identified, COFeMnSi. So you can see that the conductivity is not of a metallic system because it's increasing. It's not resistivity, it's conductivity. Then, of course, there are, you can find out various measurements we can do. This is what is the Hall. Sigma XY is a Hall. From this Hall, we can actually identify what is the anomalous contribution. Anomalous contribution is a contribution that is coming purely because of the magnetization. That happens only in the case of a ferromagnetic material. It is not proportional to the magnetic field, which is a normal Hall, but you have what is known as a magnetization dependent Hall that is called anomalous Hall. By looking at the anomalous Hall, looking at the carrier concentration, and looking at the magnetization values and so on, you can get a reasonable idea that it is actually not going to be a half metallic ferromagnet. Then if you have a theoretical support, you can actually find out what is the band structure, and that is what is done in this particular case. You can see that here, the band structure is exactly what I showed you. There is almost a zero gap for the spin up channel, and then the semiconducting properties are seen, and the spin polarization also is coming from because it's essentially a spin polarized material with a gap of zero energy. Therefore, you expect a decent spin polarization. You can see that something like 61% spin polarization as measured by the PEC-AR data. So this is one of the first EQ atomic Husserl-based system where we have seen that spin polarization is there, and also it is half metal, it's a spin gapless. So that was the kind of an attraction or the plus point at that time when we did almost 5-6 years back. It's a very interesting thing. A lot of people have tried this material because of this, and people have tried in thin films and so on. They got very interesting properties, much more than what we got also. It has become a very wonderful system that way. In fact, a similar system is there, which I'm not going to details today. A similar system, equiatomic. You see that this is also an equiatomic system. This is 1-1-1-1 system. Now, of course, there are a lot of other things going on. In fact, one can have different types of spin gapless material. This is another one, which again is equiatomic. There are different classes of materials, type 1, type 2, and so on. So we could get, you can see that spin directions are shown here. You can get the way the gap occurs, it can happen in various forms, and therefore this is what is known as type 2. In this particular case, experimentally, it's very difficult to say whether it is this or this, but with a detailed DFT with all the approximations minimized, one can actually show that in this, we could show that in this particular system, this is the kind of spin gapless nature that we have. So it's not the normal something like this one. So it's not type 1, it's type 2 in this particular case. This again almost a new finding. In fact, we have given all the details in this perspective article, which is almost like a review. If anybody is interested, you can go through that. The reference is given here. Now, as I mentioned, recently, maybe last 5-6 years, this has become very important. The antiferromagnetic or ferrimagnetic spintonics. So far, everything has been ferromagnetic. This is, in fact, in many of these conferences, there is a separate session for these antiferromagnetic spintonics. So why are we interested in this one? Because it is antiferromagnetic. Basically, the signal to noise ratio improves, especially when you are reading, because this whatever you say, ferromagnets have these stray fields. It will affect internally also the regions where the data is stored. So therefore, basically, you want to try to reduce this kind of stray field effects. It will be ideal. Of course, you need to have a magnetic order. So only way is that you have an antiferromagnetic order. So that is the reason. And also the switching speeds are much larger because the antiferromagnetic resonance, the frequency is larger. And therefore, the time scales will be, the frequency will be less. The time scale will be less. And therefore, it actually is a faster method, or it will result in faster devices. Of course, I told you that I'm not at all a device person. So one can actually do. So that is the reason why it has become very important from the actual device point of view. The antiferromagnetic materials are more sought after these days than the ferromagnetic ones. So again, which we were doing some work on this system. So what happened is that, we see that, okay, so that this is rho versus T behavior, which is not the metallic thing. Then, of course, we thought that it must be something corresponding to a spin gapless kind of thing. Then what we did was we measured the magnetization. We found that the magnetization is very low, 10 to the power of -4 is here. So it's almost very low moment. But at the same time, it has got a little bit of hysteresis. So it is some kind of it is not a clearly a antiferromagnet. Therefore, we actually thought of, okay, something is happening in the system. We did took a lot of time also to understand. So then when we did the calculation, we found that basically every individual constituent has some magnetic moment. There are actually 3 crystal configurations, non-degenerate configurations for this particular crystal structure. And then we found that the configurations are like this. They are not energetically very different. They are degenerate, but the energy separation is not very large, at least compared to room temperature. And then in all these cases, you see that the total magnetic moment is close to 0. This is a theoretical value. This is what more or less what we obtained from the experiment also. So this basically led us to conclude that, okay, this is not an antiferromagnet. In fact, actually, this material was reported to be an antiferromagnet, and with some mixture of metallic and insulate semiconducting properties and so on. But then when we did this calculation and compared with our experimental results, we could show that basically it's actually a spin gapless. The band structure has a spin gapless nature, and it actually is it's a ferrimagnet. It's nearly compensated ferrimagnet. The magnetic moments and the directions are such that the net result is 0. Of course, it's true for all the 3 configurations, and they are not very far in energy. But in any configuration, you see that the net magnetic moment is 0. So then we could conclude, of course, this is the difference between a half metallic ferromagnet, the partial density of states. If you see what is happening is that in the case of ferromagnet, it's something like ferrimagnet, it's something like this. It's a ferromagnet, it's something like that. And ferromagnet, as you know, it has got a very large internal field. It will be able to polarize all the partial bands corresponding to different elements, the constituents, whereas here you can see that it is limited to the Fermi level. So that is what is the difference between the band structure, a spin polarized band structure for a half metallic ferrimagnet versus that of a ferromagnet. So then in this particular case, we could identify that it's actually a fully compensated ferrimagnet, as I mentioned. And also it has got a magnetic semiconductor and the spin gapless semiconducting property. This is very difficult to say from the experiments, but when you do a calculation theory and compare with all the details, a lot of work is needed. We could conclude that this is actually a completely compensated spin gapless system at room temperature. So this at room temperature, the spin gapless nature wins because of the energetics is such that the energy separations are such that among the three crystal configurations of the structure, and that is what we showed some time back. Now, of course, very recently, we saw that another class of semiconductor is possible. The spin polarized magnetic semiconductor is possible. Here you can see that this is what is known as a bipolar magnetic semiconductor. What happens here? This is the top of the valence band. This is the bottom of the conduction band. You can see that they have opposite spin polarity. So that is, so if this excitation, this will be easier. So what happens is that there you have a control which is possible even with an electric field. So the polarization can be affected with the help of an electric field also, because this you can see that here the spin direction changes, and this tuning can be done with the help of an electric field also. It's a very early days today, but a lot of work is a lot of interest is there in this one. We have identified this system as one of the first systems where we could again show that it is again, you can see that the magnetic moment is very small. It has got all the properties that we expect for a semiconductor. But then from experiment, as I mentioned, you cannot tell that whether it is what kind of a semiconductor. Even, I mean, at the most, you can tell that it's a gapless semiconductor or a normal semiconductor. Nothing more than that is possible from the experimental data, even if you do it more carefully. But if you again combine with experimental and theoretical data, you will be able to show that that's exactly what happened to the system. This has got basically magnetism-wise, it's a fully compensated ferrimagnet. Very small, extremely large and small moment, and again 10 to the power of -4 Bohr magnetons, and it has got bipolar magnetic semiconducting state. So where the band structure is something like this. This is something which is very, very new, as you can see that 2021. So we have done all the transport and so on. I will not go into the details of this, just to give you a flavor that this is another kind of semiconductor that we could identify. Again, you see that's an equiatomic system. This is 1-1-1-1 composition. Very recently, again, another 1-1-1. These are all exciting things because we don't expect any of these things. But when you do the measurements, you see it always throws up some surprise. So here, of course, you see that it has got what is known as a double shifted hysteresis loop at low temperatures. So 2K. This is COFE VSB. And in fact, we have been seeing, in fact, it's a puzzle even today for us. Whenever there is vanadium, things are going to be very, very interesting for whatever reason. Of course, it actually shows some kind of a partial density of states, which is contributing to some kind of an anomalous behavior. So then you see what is known as what is like a spin wall behavior. This has been reported in very few systems where you have this magnetoresistance changes sign across as the field is changed. You see that this is a very usual spin wall feature that is expected. But that is generally seen in the case of artificial multi-layers and so on. But here there is no multi-layer. It's a single bulk polycrystalline material, but we are seeing features corresponding to that. So this is very interesting. This is again very recent data. But interestingly, okay, we would have been happy with this. But then what happens is that if you, I mean, I don't remember even what was the context of measuring the thermopower here. When we measure thermopower, we find that the thermopower is very unusually large. If you see that it's something like, so that square sigma, which is, of course, we are yet to get the thermal conductivity for problem of COVID and so on. So a square sigma, which is found to be something like 800 in this unit, is much larger than what is seen in any of the materials. Even a good thermoelectric, you don't, I mean, the decent thermoelectrics, you don't get this one. So again, something which is happening here in this particular case. So it's something like a effect which two effects are happening here. One is the spin wall effect, which itself is very rare. But then it has also got, we don't see there is any connection between the two, but it has also got a good thermoelectric thing. So it is promising. Actually, it is not even saturating, it's going on. So if you go to higher temperature, it may even go up. We are yet to get some more data on that. And therefore, this is going to be promising in some sense, even from the thermo point of view. But of course, now the interest is to see whether it has got some kind of a spin analog part of these thermoelectric properties. That is what we are trying to do. We are trying to get some collaborator and do some of these measurements, which are probably going on right now. Then again, another class which I mentioned, it's a semi-metal. I'll not go into the details here because I think my time is almost getting over, I think. So what happens is that in semi-metals, we know that you have electrons and holes as carriers at the Fermi level. but it happens only for one type of spins, then one can define what is known as a spin semi-metal. The spin polarized semi-metal, that's the meaning of that. Very, very few reports were available when we did this compound. It was again, we thought it will be a half metallic ferromagnet. That is how all our investigations generally start. And then from the conductivity, we see that, okay, it's something like a semiconductor. Then usual suspects are whether it is a spin gapless, because now we have had some experience at that time, or it's a normal, like a magnetic semiconductor. Or then we, again, I mean, this was actually done. In fact, there was a question earlier, right? This is done pure, the band structure was purely done using quantum espresso. My student was very keen to do that. And he could show that it actually, maybe it is something like a semi-metal. So experimental data, you have the normal things only, which will not be able to distinguish among the three. We will not be able to say that. But with the calculations, we could see that it actually has, for the one type of spin, that upspin, there you have carriers of both electrons and holes at the Fermi level. Therefore, we identified this as probably the first spin polarized semi-metal. Again, combining the experimental and theoretical data, which was again very time-consuming thing. Not only, so basically the point is that, okay, is it a spin polarized semi-metal? From the experiment and theory, even at that time when we were publishing it, we were not sure. Maybe that's why this question mark is probably still relevant. But interest was not over there. When we actually plotted, we could see that it actually has some kind of a topological thing, because it has got these kind of Dirac cones, which was very new at that time. So we found that it's not only spin polarized semi-metal, which itself is a new class, but then it also has wild features. It has to be wild because it's a magnetic thing. I mean, again, something which is little tricky even today. So it is having some kind of a topological feature as far as a band structure is concerned. But of course, we don't have any experimental data for this to be proved. But definitely it is kind of resembling some kind of topological things. And of course, the spin polarized semi-metallic status. So that is what is published here. This is a pure quantum espresso calculation, and the student has done a lot of, taken a lot of efforts to do that. And these are all the things which kind of convinced us that, okay, it must be something like a wild semi-metal in this particular case. In fact, at that time, we are not even clear about our literature. So then we looked at the literature, then we saw that, okay, there is a possibility, because fuselars are known to show these kind of different types of topological materials. It can be topological insulators, very few of them. Then you can have Dirac, or you can have the while. While means the time reversal symmetry, or the inversion symmetry is broken. So, or basically it is magnetic. Most of the magnetic, ferromagnetic things, you can get topological features. That means a wild semi-metal. So if you have a semi-metallic property, you can reasonably doubt that it must be a wild feature that is coexisting, at least coexisting with the other features of spintonic aspects. So this was a kind of relief for us, because, okay, there is a possibility that it can be. So that was the kind of confidence with which we were able to communicate this, and the referee was also not very critical, and it was accepted. So basically, this is a very interesting thing in the sense that it is a spin polarized semi-metal, which is very interesting as far as a very highly specialized material. But then it also has its topological features, which is making it very, very special. So we are trying to do some more measurements and trying to get other aspects of this from the topological part. Unfortunately, you should remember that all the samples I have shown so far, everything is a polycrystalline sample. Therefore, the information that you get will be quite limited. Professor Santosh probably will know that the data, the quality of data and the information, the data richness will be very different if you have single crystals of this. Unfortunately, it's not very easy to grow many of these single crystals. Okay, from the topological thing, we started looking at it. Then we found that there are possibilities of even the spin gapless semiconductors. You can have this, instead of these parabolic bands, of course, the schematic, you can have these linearly dispersed bands. That will be interesting. So there are some reports, not from the Husserl family, but there are things. So we are trying to see whether something of this kind is possible. Magnetic, non-magnetic, wild, Dirac, and so on. So this topology that we talk about is in the K space, as I mentioned. The topological materials, when we say, we are talking about the topology of the K space. But as I mentioned, you can also have topologically protected states in the real space itself. The spin configurations can be protected because of a particular topological nature, and that actually gives rise to magnetic skyrmions. Different kinds of very funny shapes. In fact, this list can be extended further. There are many, many possibilities: skyrmions, biskyrmions, merons, antiskyrmions, and so on. Various possibilities of these are all magnetic, basically spins having a particular thing. They are very stable. the size is very limited. That's a challenge today. And the temperatures and the field ranges are very small, very limited. But if you can get some of these features at room temperature with a reasonable field stability and thermal stability, it's very, very wonderful. They are kind of wonder materials for recording and so on. So a lot of interest, a lot of work is being done. So this is the topology. So basically, I talked about Berry phase earlier, which is very important aspect of the topological materials. But now you have a corresponding Berry phase or Berry contribution coming from the real space. That is what is happening here. So there are various issues. I talked about the anomalous Hall, which is coming from the topology of the band structure that gives rise to anomalous Hall effect. But here the band structure, I mean, the real space ordering of this particular shape, that's the topologically protected state in the real space gives rise to another contribution to the Hall called the topological Hall effect. Topological Hall effect usually comes from this kind of magnetic textures, which are very, very important today. So a lot of things are going on. So we have started this, we have got some very preliminary data, I'm not showing it. So basically a lot of work is being done to identify newer material. There are certain restrictions as far as the crystal symmetry is concerned, because originally people thought that centrosymmetric systems will not show, because usually it is dominated by the DM interactions. As you know, that DM interactions will not survive when there is a center of symmetry. But that's also not really true. People have proved that even in systems of that kind, you can actually stabilize fermions. So we are actually looking at both centrosymmetric and non-centrosymmetric systems to see whether you will be able to stabilize some of these things, at least at low temperatures and some field ranges. And so that work is going on. So I'm not able to present something which is worthwhile at this point of time. So this is especially, my thing is that especially those who are working in magnetism, if you are actually getting some kind of a conical arrangement, modulated structures of this kind, you should seriously doubt, and you should do some more experiments to see whether it actually corresponds to these kind of magnetic fermions and so on. So this is basically possible. So this is, thing which is already known, that Husserl materials are known to various kinds, as I mentioned, anomalous Hall effect, spin Hall effects, fermions, the usual topological aspects. All these things are possible from the same family, and therefore it is a very versatile family, something like the oxide family, which we knew almost 3 decades back. There are many interesting physical properties which can be measured. One of them is what is known as the chiral anomaly, which is very interesting from the point of view of high energy physics also. People are very keen to find out what is happening in the condensed matter community, the research, and that will be very useful for them. So this is something where it's not like a Hall. You have the magnetic field and current in the same plane, and it gives rise to a particular shape of the magnetoresistance. So people are looking for topological superconductors, again, from possibility from this family. The thing is that people think that, okay, Majorana fermions can be seen in systems like that. As I mentioned, chiral anomaly is something which people have already seen in this half Husserl system, GDPT, BI search is going on to see several new systems and so on. So that is why the interest is not just confined to condensed matter. It is cutting across topics of physics. So conclude. So adding, what we have done is basically we added the spin degree of freedom, and that actually has tremendous consequences, as you have seen, not only from the point of view of spintonics, but is actually stretching to the topological aspects, both in the K space and the real space. So it's an ideal platform to realize certain things of things like what we know, what we hear. For example, this massless fermions and so on, which are really relativistic quantum mechanical terms and ideas, which can be tested the point of view of using the platform of condensed matter physics, using these materials, namely the Husserl systems. So let me thank my students, postdocs, and so on, and also my collaborators. So thank you all for your patience. Thank you very much.
Thank you very much, Professor Suresh. Audience, do you have questions? If you have questions, can you please unmute yourself and ask? Okay, let me thank you once again for bringing quite large variety of model systems from this Husserl family. So I just have a couple of questions. You mentioned about this absence of magnonic contribution in resistivity, and we looked at the result of this cobalt to iron chromium silicon system. So you have shown basically 2 temperature ranges in, I think, 100K to 300K. We had pure T-square dependence, and below 100 up to 50. We also had a higher order term.
Yeah.
What is that signifying? T power 9/2.
Yeah. So what happens is that you see, when it is a ferromagnet and antiferromagnet, the dependence are different. So basically, if you have some kind of contribution which is mixing the two, it will be very difficult to see even that 3/2 and some very close power. It's very difficult. That's why I don't really believe this power law fittings beyond a point. It's extremely tricky that especially these systems where the complexity is much more. So identifying anything just based on the fitting of this resistivity data, I myself am having my own doubts, because it's first of all, as you mentioned rightly, the temperature range. How do you decide the temperature range? That again, sometimes it is up to your convenience, right? That is also a problem. So that is why just based on the resistivity fitting, I mean, that can be used as a supporting evidence, but it should not be taken as a concrete evidence. Obviously, that the fitting is going to be very, I mean, if I make slight change in the power, things can be very different. So I think that should be taken with a pinch of salt. The fitting of the resistivity, especially at low temperatures. High temperatures, things are okay. The real contributions will be mostly phononic. But at the low temperatures, you can actually have an electron contribution, which also has a t-square dependence, by the way. So that also can create problem. That actually can add to this one. So you will be thinking that, okay, it's something like a 9/2, but actually that may be a t-square and something else. Extremely tricky that you should not depend on that. You can just use it as a supporting thing.
Thank you very much. You also mentioned about doing calculations and getting this rho of T, right? Have you succeeded in getting?
In very few systems, yes.
In very few systems.
Yeah, they do some other, versions of the DFT. Professor Aftab does for me. So it is, I mean, very few systems. Of course, we have simulated, definitely 3 systems, we have the data. And there, the experimental theory agreement was not bad. I will say it was not bad. But of course, I think Nanda can do. I think so. Yes.
Thank you. There is one question from, I think, audience, Dr. Alagunambi. He's asking, do you have any oxide impurities formed in the system?
That is sometimes asked by the referees, especially when you go to some of these anomalous properties. What we have seen that in many of the things, I did not show that we do EDAX. And we have not seen anything that worthwhile. And also we tried to see what magnetic transition temperature and so on. At least we could not really see any peak corresponding to those oxides, whatever suspected oxides one can think of. So usually we have not seen, but again, something which I cannot 100% rule out, because these are all metallic systems. You are dealing with metallic systems. We take all the care, but how much is the care that one can do? That is, but of course we use vacuum desiccator, minimum exposure and so on. But yes. I will say that, I mean, reasonably they are pure.
Thank you so much once again. I think it was a very vast topic. You brought us many features of this useless systems. Thank you very much. Thanks also on behalf of the organizers.
Thank you.
I think next we will move on to the
Anil has already gone.
Professor Anil Kumar. Professor of Physics, Indian Institute of Science, Bangalore. I'm very glad that organizers have arranged the 3 talks in such a sequence. We had Professor Santosh, Professor KG Suresh, and now Professor PS Anil Kumar. We can call them forming a group of 3 magneticians. So we have become kind of complete today in this session. So what I hear from Professor Anil is that he has come back to give this talk at his alma mater. So he is actually a student of Fatima Mada College long ago. So welcome. So that's a very interesting thing, right? And I will say a few words about Professor Anil Kumar. He has graduated from University of Pune. So after his PhD, he went on to do postdoctoral research at the University of Twente in the Netherlands with the DTF Foundation Fellowship. Then he moved to Max Planck Institute for Microstructural Physics with a DAD Fellowship. And then he came back to Indian Institute of Science, and where he is currently a professor. So Professor Anil Kumar is well known for setting up contemporary experiments in condensed matter physics, particularly in magnetism, as you will see in today's talk as well. So he's a very accomplished researcher as well as a very able administrator. So, and his interests are covering a wide range of topics, including spintronics, magnetic nanostructures, and multi-layers, and so on, very low dimensional systems, and so on. And today he'll talk about magnetization reversal again, but this time it is current induced in heterostructures of ferromagnets and heavy metals. Over to you, Professor Anil. I think you are muted.
Can you hear me?
Yes, yeah. Sure.
Okay. Okay. So thank you, Dr. Nirmala, and I thank you for the nice introduction. Let me thank Dr. Sunil and Dr. Shaina and other members of the Department of Physics for inviting me to this conference. As Dr. Nirmala said, this is my alma mater. I did my pre-degree as well as degree from Fatima College. I passed out in 1990 from Fatima College. So thank you. And today I'll be talking about current-induced magnetization reversal. As time progresses, you will realize what do I mean by current-induced magnetization reversal. So this work was initiated by Dr. Vineet Mohanan, who is now an assistant professor at Cochin University of Science and Technology in the physics department, and continued by Mr. Shauvik Kyle, who will be defending his thesis in a week's time. And this work is supported by various funding agencies, Nanomission, then Department of Atomic Energy, Max Planck Society, National Nanofabrication Center at IISc, etc. So let us now start with some very fundamental aspects. Let me share this. So let us start with some very fundamental aspect. Now, you consider a ferromagnetic material and you apply a magnetic field. You must have seen in the 12th standard textbook what is called the hysteresis loop. You have this hysteresis loop, which is a curved kind of thing. Now, I'm going one step further. I say that I have a single crystal material which has got something called easy axis of magnetization and hard axis of magnetization. The name itself suggests that easy axis of magnetization means it is easy to magnetize a material along the easy axis of magnetization. For example, if I take this pen, I mean, imagine this is a single crystal and this is the easy axis of magnetization. Now, if I apply the magnetic field along the easy axis of magnetization, and if I measure the magnetic moment, you see that if I apply sufficiently high magnetic field, the magnetization is here. Now, even if I remove this magnetic field back to zero, reduce it back to zero, still it will have 100% remanence. So it is fully magnetized. And if I reverse this magnetic field and then go to the negative direction, above a critical field, the magnetization reverses from plus M to minus M. And this is called the magnetization reversal. And this field is known as the critical field or the cozy field of this material. Now, if you increase further and you get this saturation here, and when you come back again, full magnetization, and again you reverse it, and you get this hysteresis loop. And if you consider now, instead of applying the magnetic field along the easy axis, if I start applying the magnetic field along the hard axis, what happens? At zero magnetic field, all the magnetic moments are in this direction, so there's no component of magnetization in that direction. But if I start applying a magnetic field, what happens? The magnetic moments start aligning in the direction of the applied magnetic field. And finally, all the moments get aligned in the direction of the applied magnetic field. Then it gets saturated. So this saturation and this saturation value will be, in terms of magnitude, will be same. But if you start reducing this magnetic field, what happens? One by one, the magnetic moments will go back to its easy direction. And finally, at zero applied magnetic field, you have zero magnetization. And if you go to the negative side, again, it gets saturated. But this is called a linear response, which is generally used for sensor applications. And this is hysteresis that is used for memory application. So today's talk, I'll be discussing about this memory applications of this magnetic materials, ferromagnetic materials. Now, you may wonder then why in the 12th standard textbook, neither of these two graphs are there, only kind of a slanted hysteresis loop is there. Actually, those things are a collection of particles. So it's a polycrystalline material, which has got collection of particles, and those particles are randomly oriented. Some particles are oriented in this direction, some in this direction, some in this direction. So when you collect all these particles together, it will be like a sum over of all the different directions. This is one preferred direction. This is the hard direction. So whereas the hysteresis loop, which you see, is a sum over everything. So that's why you get this curved hysteresis loop. Now, why do we talk about magnetization reversal here? And all of you, including me right now, I'm talking, is using magnetization reversal spontaneously. In the sense that right now when I'm using a computer, I'm using a computer hard disk. The hard disk has got information stored in magnetic bits. Say, for example, what is your hard disk? The hard disk is nothing but millions of magnets assembled in a particular way. Now, suppose if I have a magnet with this magnetized, this cap as the north pole, and this is the south pole. When I say this magnet is magnetized upward or the north pole is upward, I can define that this is a one state of this magnet. Now, if I change it to the down direction, then I can say this is a zero state. So I can define a one state or a zero state with one magnet. Now, if I have two magnets, if I put both the north poles upward, I have one state. And if I change it like this, I have 1 0 state. If I change it like this, I have 0 0 state. Now, instead of 3, I have 4 magnets. I can define 1 1 1 1, 1 1 1 0, 1 1 0 0, 1 0 0 0, 0 0 0 like that. So this is how I store information in my computer hard disk in terms of bit. Now, if you look at your hard disk, do I hear some disturbance?
I request the audience to keep themselves muted, please.
Thank you. So now if you consider your hard disk, these bits are, magnetized upward, north pole upward or downward, and this information is stored as zeros and ones. Now, how do I change? With this pen, I could just revert it like this, and they say that, okay, one state has gone to zero state. But in a computer hard disk, you cannot go and pick every magnet and reverse it. So there should be a mechanism of reversing the magnetization. If you remember the hysteresis loop I showed you, if I apply plus H magnetic field, which is higher than the coercivity, it is in the plus M state. That means magnetized upwards. Now, if I apply a magnetic field in the minus H, in the negative direction, more than the coercive field, then the magnetization switches down. This is what is happening in your computer hard disk. So here you have a writing element. You have a yoke like this. This is like, if you take a screwdriver and wind a wire around it and pass some plus I current, you see that a magnetic field is generated like North Pole like that. If you reverse the current, it magnetizes in the opposite direction. Same thing similar to that. You have a yoke where there is a wire wound around this. And if you apply plus I current, it creates a magnetic field. And this is a broader one to close the flex. And locally, you can apply a magnetic field which is higher than the coercivity of this material. And if I apply plus I current, plus H field, magnetization is upward. And if I apply minus I current, minus HC field, and the magnetization is reversed. So you can switch the magnetization up and down. That's what when you try to write something in a hard disk, you hear a sound. The sound is coming because there is a plate. It's a circular plate which is rotating. And this right disk is on top of it, and each bit is aligned on top of this right head, and you decide whether you want to write plus 1 or 0. So plus I current or minus I current. Then the next bit comes, you again write plus I or minus I, plus I or minus I. So like that, each bit comes below this right head, and you write the information zeros and ones. That is precisely what is happening when you try to write information in your computer hard disk. Now, here, what I do is that I create a magnetic field by passing electric current through a coil, and that electric current creates a magnetic field, and that magnetic field is switching the magnetization. It is a very energy inefficient process. So people thought that, can there be a method to switch the magnetization by electrical current directly? So people found that there is a mechanism called spin transfer torque, where you create a beam of spin polarized electrons and it passes through this material. And in this part of the material, the magnetization is in this direction. This part of the material, magnetization is in this direction. Now, if I pass a current of spin polarized electrons, what is spin polarized electron? you have a mix of upspin and downspin electron. Now, predominantly one type of electrons I choose, and by pass through this material, what can happen? By separating these two magnetization, there is something called a magnetic domain wall. This spins exert a torque on this material, and then it pushes this magnetic domain wall. Finally, if I push this magnetic domain wall completely to the other side, my entire material is magnetized in this direction. Now, if I push this magnetic domain wall extremely to that end, then I magnetize in that direction. So that means it was shown that it is possible to switch the magnetization from one state to the other state by passing electrical current, spin polarized current through the material. And the current density that is required to switch this magnetization is 10 to the power 8 ampere per centimeter square, or 10 to the power 12 ampere per meter square. It's a huge current, right? So here comes the advantage of this dimension, centimeter square. So I can make the dimension of my system much smaller, so that the current density can be maintained, but the switching can happen, right? And this has got several applications. In the sense, you can talk about something called a racetrack memory, where you can store multiple bits of information in one track and then move this magnetic domain walls up and down. And when the red domain comes here, it will give a 0 state. When the blue domain comes here, it's a 1 state. So you can define zeros and ones depending upon whether it is magnetized in that direction or this direction. So multiple bits can be stored. Another interesting application is something called magnetic random access memory. Right now we have random access memory in our computer, which is volatile. That means it needs a battery backup. If you remove the battery from your memory device, the information is lost. So the next generation magnetic random access memory is a non-volatile memory. So means you don't lose this information even if you don't have a backup, a power backup. So that means you can have random access memory which is non-volatile. And people thought that you can make a multi-layer structure with tri-layer structure with the two ferromagnets separated by a non-ferromagnetic metallic layer. And when the two magnetizations of the two ferromagnetic layers are parallel, I call it as a 0 state. When they're anti-parallel, I can call it as a 1 state. How do I know whether they are parallel or anti-parallel? The resistance of the parallel state is lower compared to the resistance of the anti-parallel state. And just by measuring the resistance, I'm in a position to find out whether it's a 0 state or 1 state. So it is a non-volatile memory plus a read disk, hard disk, a read head need not go everywhere. So it has got its own wirings. By passing electrical current through this, I can switch the magnetization. And by measuring the resistance of the ith row, jth column, I can find out whether it's a 0 state or a 1 state. So there is no moving part. There's no non-volatility here, or it's a volatility here. So in that sense, this MRAM is going to be a very potential important device for future. And people found that you can have magnetization switching by this spin transfer torque, but unfortunately the current required to switch this magnetization is 10 power 8 ampere per centimeter square. In this kind of structures, you need to have a transistor connected to each of this bit for the selectivity. And these transistors cannot afford to withstand this much kind of electrical current. So there is a requirement for making systems where the current required to switch the magnetization is much lower. So that is why people started looking at alternate ways of creating spin current. So let me just bring to your attention the Hall effect. All of us know, if I pass an electrical current through a material, and if I apply a magnetic field perpendicular to that and perpendicular to both these directions, an electric field will be generated, and this is the Hall voltage. So this was discovered in 1879. And later on in 1881, it was found that if I take a ferromagnetic material, I don't need to apply a magnetic field. I can pass a current. If the magnetization is upward, then there will be accumulation of positive and negative charges here, so that there will be a voltage generated here. Now, if the magnetization is reversed, this voltage sign changes. So here you needed a magnetic field for a non-ferromagnetic material. For a ferromagnetic material, you don't need magnetic field, and it is called anomalous Hall effect. Now, if I consider in 2004, it was shown that there is something called a spin Hall effect. So what does it mean? It means that if I have a beam of electrons passing through a heavy metal, HM means heavy metal, the electrons of one type will get accumulated onto one side, the electrons of the other type will accumulate to the other side, and you can have a separation of spins. So upspin electrons will accumulate in this direction, and the downspin electrons will get accumulated in this direction. You remember, for the spin transfer torque, what we needed was a spin polarized current. Now, what is the consequence? Now, if I take a material, a heavy metal like tantalum, platinum, iridium, those kind of heavy metals, and if I pass electrical current through it, to begin with, it is connected to a copper wire. When the copper wire injects electrons into the system, it is unpolarized electron. But when these electrons pass through this material, electrons of one type will get accumulated to the top surface, the opposite type on the bottom surface. One type on the side surface, the opposite on the other side. Now, this material, instead of a three-dimensional structure, if I make it a two-dimensional, I make a thin film, what happens? If I pass electrical current, one type of spins will get accumulated on the top surface, and the other opposite type of spins will get accumulated at the bottom surface. And then this we can define the efficiency of this is called spin Hall angle. That means the spin Hall angle is the amount of spin current you have generated divided by the charge current. Platinum has got an efficiency of 0.1. So that means you have a ratio of spin current to charge current is 0.1 in platinum. So you will see that in the remaining part of the talk, I will be discussing about platinum. So now what we will do, you have a platinum layer. On top of the platinum layer, I deposit a cobalt layer, which is magnetized perpendicular to the plane of the system. And if I pass electrical current, then this electrical current will accumulate spins on this surface, and these spins will exert a torque on this ferromagnetic material, and that torque will switch the magnetization. So this is called, this scattering, this spin Hall effect is coming due to spin orbit interaction in the heavy metal, because heavier the material, the higher the spin orbit interaction. And because of this, it's called a spin, it's originating from the spin orbit, and this torque is called spin orbit torque, right? So now let me set the motivation. For the spin transfer torque, you need 10 to the power 12 ampere per meter square as a switching current, and you wanted to develop materials that can be switched with much lower electrical current. If I am reducing the electrical current by a factor of 10, I'm saving the electrical power by a factor of 100. Because when you pass electrical current through these structures, there is something called Joule heating. So the Joule heating is I squared R. So where I is the current, if you can reduce the current by a factor of 10, since I square is there, I can reduce the power consumption or the power dissipation or loss by a factor of 100. So that is very relevant. In this today's world, generating more and more energy is an important aspect, solar energy, wind energy, hydrogen energy, all those kind of things. We are looking in a different way, making devices that consumes less electrical power. If you look at the data centers, 80% of the power in the data center is used for cooling the equipments, because a lot of heat is generated, and the data processing will not consume that much power, but the heat generated in that process need to be removed. So that means efficient cooling is needed. That's why Google has started a data center in Antarctica, because there you get cool, cheap cooling power. So the idea is to make devices that consume much lower power. And the state, I just wanted to tell you that this 10 power 12 ampere per meter square has been successively reduced to say 4 into 10 power 11 ampere per meter square, an order of magnitude by this spin orbit torque. So in today's discussion, I'll be discussing about the quest for designing a heavy metal ferromagnet, heavy metal based heterostructure to make low power consuming devices. So let us do a tutorial here with some case studies. So we make all these films, say for example, platinum, cobalt, platinum, which is heavy metal, ferromagnet, heavy metal by sputter deposition. So this is an homemade ultra high vacuum sputter deposition system, which has got multiple targets associated with it, and you have efficient pumping stations. And this is the equipment, which is designed by us and in-house made. And this is in a class 1000 clean room. So you have all the sputtering guns here. You load the sample through a load lock. You load the sample through a load lock, and then you do the deposition inside, and the base pressure is always at the better side of 10 power minus 8, and you can bring the system down to minus 10, minus 11 millibar vacuum. Now with this kind of a structure, so let us deposit some films. So you say that I have a silicon dioxide substrate. So I just show only silicon dioxide here. And you deposit 4 nanometers of platinum. Then you just deposit 0.44 nanometers of cobalt, and then cap it with 1 nanometers of platinum. So now if I measure, what I measure is something called a magneto-optical Kerr effect. I can do a vibrating sample magnetometer measurement or a squid magnetometer measurement for magnetization. Here, what I chose to do is something called Kerr rotation. Suppose if I have a plain polarized light, which is hitting on the surface of a material, and there is a reflected light where if it is a non-ferromagnetic material or the material has got net zero magnetization, the plane of polarization will remain same even after the reflection. But if this material is ferromagnetic, then the reflected beam will have a slight change in its plane of polarization with respect to the incident angle, and the rotation is called the Kerr rotation, and that Kerr rotation is proportional to the magnetization. Now, if I measure the Kerr rotation as a function of applied magnetic field, I will get the magnetization versus applied magnetic field curve. You can see here, this is the Kerr rotation. And for this structure, you see that when you apply 120 oersted field, it gets magnetized in the upward direction. And when I bring the field back to 0, and the magnetization is almost 100% there. So this is exactly similar to the hysteresis loop I showed you in the beginning. And when I go to the negative side and I apply a larger magnetic field, it switches its magnetization down like this, and you get this hysteresis loop, right? So this is not just like that. So suppose if I vary the cobalt layer thickness between the 2 platinum layers, you see that there is a critical thickness below which the cobalt is magnetized perpendicular. So above 0.8 nanometer, 0.9 nanometer, the magnetization goes in plane. So between a small window of 0.3, 0.4 nanometers to say 0.8 nanometer, the magnetization of this ferromagnet is perpendicular to the plane, which is cobalt is perpendicular to the plane. So this is the setup for this magneto-optical Kerr effect. So you have polarized light which is falling on here. You analyze the polarization of the reflected light, and then you plot the rotation. That means the change in the polarization axis as a function of applied magnetic field, and you get all this hysteresis loop. And also, it's very important to grow very high quality metallic layers to get this phenomena. You see here, I'm just having only 0.35 nanometers of cobalt layer. And if I vary the platinum layer thickness between 2 nanometers to 8 nanometer, if I plot the magnetization, this is a squid magnetometer measurement, magnetization versus temperature, you see that the magnetization, the TC of the material is going above room temperature in case when I have 8 nanometers of platinum. Whereas if I add a tantalum layer below this platinum layer, you see that I can increase the TC even with 0.3, just 3 nanometers of platinum and 0.35 nanometers of cobalt, the TC is above room temperature. But if I go even to 0.26 nanometers of cobalt, you see that you see a ferromagnetism, whereas the TC is below the room temperature. So I'm looking for TC above the room temperature because all the experiments which I'm going to show you is at room temperature experiments. So I don't want to show you low temperature experiments. And also you see that the magnetization of this material is almost like 2000 EMU per cc, whereas you know that bulk cobalt has got only 1400 EMU per cc. So where is this additional 600 EMU per cc coming? We have other experiments which shows that this cobalt induces ferromagnetism, magnetic moment in platinum, and the platinum moment is adding to this magnetization here. That's how it is coming. So these are all corroborated with high resolution X-ray diffraction studies. And now to show you how this magnetization reversal happens, I told you about magneto-optical Kerr effect. Now I can do a magneto-optical Kerr microscopy. That means this, like a microscope, I look at the reflected light coming from different regions, and by mapping the rotation of that, I can map the magnetic domains of this material. So this is what I'm going to do here. And also, since I wanted to do current-induced magnetization reversal, we also have a electrical setup attached to this one to apply electrical current and see the magnetization reversal. Now look at this curve. So what I had was silicon, silicon dioxide, platinum, cobalt, tantalum, platinum, cobalt, platinum layer. And then I do a lithography and I remove unwanted material from this layer. And now the black region is the only one that has got tantalum, platinum, cobalt, platinum layer. Whereas this area, what I'm seeing is bare silicon dioxide. So the material is removed from this by doing optical lithography and the etching process. And now if I do this Kerr microscopy, what I see is that dark color means magnetization is towards you, and the light color means magnetization is towards me. So this is a film, it's magnetized upward is the dark color, magnetized downward is the white color. So you see now, at any data point you consider, any pixel you consider, and if you plot this magnetization versus, this Kerr rotation by this applied magnetic field, you get this kind of hysteresis loop. So this is this is a field-induced magnetization reversal, because I am applying the applied field is HZ, which is perpendicular to the plane. Now the same system, now I pass electrical current through this. And when I pass electrical current through this, you see that I am switching the magnetization from dark to white only in this small patch. Why is it so? As I told you earlier, what is needed is a critical current density to switch the magnetization. The current density, not the current. So the current density in this region is maximum because this is the lowest dimension structure. Whereas here, the size is bigger. So the denominator is bigger. You need higher current to switch the magnetization in this region. Now, if I concentrate on this region, and if I plot the applied current versus the magnetic field, magnetization, you see that I apply an electric current, everything is magnetized upward. I reverse the current and I come to the negative current. Above a critical current, I switch the magnetization downward. And this current is called the critical current. And this critical current density in this particular case is 3 into 10 power 7 ampere per centimeter square, or 3 into 10 power 11 ampere per meter square. Already you have one order of magnitude lower critical current compared to the spin transfer torque. So this is the concept. So I just wanted to show you in the next 5 minutes or so, 5-10 minutes, how do we engineer the material further to reduce the critical current density. Now you see that as time progresses, you will have more complexity on the structure. So you have different types of samples generated. The first sample, just concentrate on this. The first sample has, okay, now I moved from cobalt to cobalt and boron, another ferromagnetic material, tantalum, platinum, cobalt and boron, platinum, tantalum, platinum. Now, when it comes to the next sample, you see that this cobalt and boron is not a uniform layer. It is slightly having a thickness gradient. But when you ask me about the thickness gradient here, this is the devices I'm going to tell you about is 100 micrometer structure. If I take 1 centimeter long of this structure, here if I have 50 nanometers, 40 nanometers of COFEB, this end it will be only 45 nanometers of COFEB. So the figure is little bit misguiding, it is exaggerating. But actually, when I reduce the dimension to 0.5 nanometer, I will not even have an atomic step extra here. So what I can just say that few extra cobalt and boron atoms here compared to this side. That's it. Now, when I come to the next structure, I keep the uniform cobalt and boron, but now I put a very thick cobalt and boron on the top. There is a reason for it, which I will tell you. And when it comes to the next structure, the gradient plus this thick cobalt and boron. Now, when I talk about this multi-layer structures, we intend to deposit a particular thickness. Then, generally we do very periodic calibration to make sure that we have the exact thicknesses. But in spite of that, we still verify the thickness of each film that deposit by X-ray reflectivity. So this is the X-ray reflectivity data, and this is the fitted curve. From the fitted curve, I can get the thickness. I wanted to put 2 nanometers of tantalum. Instead of that, it is 1.99. I wanted to put 3 nanometers of platinum. Instead of that, it is 2.83. I wanted to put 0.6 nanometers of cobalt and boron. It is 0.61. And I wanted to put 0.5 nanometers of platinum. It is 0.55, like that. So for every film which I'm going to discuss, we have done this X-ray reflectivity, and you can extract a lot of parameters from X-ray reflectivity. The thickness of the individual layers, the interface roughness. The interface roughness should be extremely small to see this kind of effects. You saw, I am just talking about 0.3, 0.4, 0.5 nanometers. That means 3, 4, 5 angstroms of a layer. And if the surface roughness is much more than that, it can destroy the properties. Now, let us now look at this structure. And I am making this kind of a hall bar. And now I am applying an electrical current. Now in this particular structure, I am applying an in-plane magnetic field. And in presence of an in-plane magnetic field, I am applying say 4 millitesla magnetic field in plane. And I plot the exactly same curve as I showed you earlier. I get a critical current density here. Now if I remove this in-plane magnetic field, you see that the magnetization reversal is not complete. So that means in the absence of a magnetic field, I'm not getting the magnetization reversal in this kind of structure. So if I apply more magnetic field, like 60 millitesla in plane field, the critical current density is well defined here. Now I can generate a phase diagram, which is called a switching phase diagram, where I plot this in plane applied magnetic field with the critical current density. You see that when I apply zero magnetic field, I don't get a magnetization reversal. So here also, I need to apply an in-plane magnetic field to get magnetization reversal, but I'm getting this thing at 1 into 10 power 11 ampere per meter square. And now what I do, I go to the next device. Let me try to move this. Maybe. So. Oh, okay, sorry. Okay, so now I have applied a very small thickness gradient, and now I can make a device which is along the thickness gradient direction or perpendicular to the thickness gradient direction. Now, if I do the measurement along the thickness gradient direction, I still see that I need a magnetic field to be applied to get magnetization reversal. So if you look at the switching phase diagram, at zero applied magnetic field, there's a gray area, means I'm unable to switch the magnetizations. Now I go to the next structure. I go to the next one, which is perpendicular to the thickness gradient direction. Here you suddenly see that even without applying a magnetic field, I'm able to switch the magnetization by applying pure electrical current from plus M state to minus M state. And also now if you look at the switching phase diagram, there is no gray area here, and even at zero field, I'm able to switch the magnetization. Now I have come to a situation where just by applying electrical current, because of a small thickness gradient, I am able to switch the magnetization. Now I go to another structure. See, for example, now I'm going to put a cobalt and boron. See, in the previous one, you saw that when I applied the magnetic field along the thickness gradient direction, I had to apply an in-plane magnetic field. Now, my question is that, okay, can we apply an in-plane magnetic field just by putting a ferromagnetic material near to that? So that if I have a ferromagnetic material which is in-plane magnetized, you know that there will be stray magnetic fields, and that stray magnetic field couple of nanometer away can give an equivalent in-plane magnetic field. And indeed, that is what you are seeing here. In this kind of a scenario, even when I apply the structure along the thickness gradient direction, even at zero applied magnetic field, I'm able to switch the magnetization. So now just by adding a ferromagnetic layer, that is substituting the requirement of applying an in-plane magnetic field. Now, along the other direction, it is always there. Now, what do we achieve with this kind of a structure so far? See, look at the last curve here. we are now able to switch the magnetization at a current of 3.35 into 10 power 10. Imagine the first transparency I showed you, 5 into 10 power 11, 3 into 10 power 11, now 3 into 10 power 10. 1 order of magnitude reduction in the current, and 2 orders of magnitude reduction in the current with respect to spin transfer torque. So this is the improvement. And so what we achieved so far is 3.35 into 10 power 10 here. Maybe I will just conclude with one more transparency. So this is the structure that we were looking at. Now what we did was we started putting a very thin layer of platinum and a thicker layer of tantalum on top of it. There is a reason. When you pass electrical current through this, the platinum has got a positive spin Hall angle and one type of electrons get accumulated. And when you have another platinum layer on the top, the opposite type of spin get accumulated and they can get cancelled each other. So we wanted to put a material whose spin Hall angle is just opposite to the platinum, which is tantalum. But when we put tantalum directly on COFEB, that destroys the COFEB. So we just put a very, very thin, discontinuous layer of platinum, and still this tantalum is not destroying the cobalt and boron, and at the same time, it gives the negative spin Hall angle. So that is the aim. With again, we do all this X-ray reflectivity and understand everything. Now you can see that in this kind of a structure, even at zero magnetic field, you are able to switch. Now the critical current that is needed to switch has gone down further. And there is no gray region. That means without applying an in-plane magnetic field, you are able to switch the magnetization. So the state of art right now, what we have achieved up to is less than 2 into 10 power 10 ampere per meter square. So our search is going on to expand the complexity of this and exploit different kinds of physics and use it here to reduce this current further so that the future spintronic devices will be consuming less electrical power. So the summary, I just showed you that there is a spin Hall mediated current induced magnetization reversal. That means without applying a magnetic field, I'm able to switch the magnetization of a ferromagnetic material from an up magnetized state to a down magnetized state. And by proper engineering of the interfaces and the layers, we have now reached a number which is 1.9 into 10 power 10 ampere per meter square at 0 bias field and 60 millitesla respectively. So thank you for your attention. This is my group prior to the COVID breakdown. So it was in front of the physics department. Thank you all.
Thank you very much, Professor Anil. Do we have any questions for Professor Anil Kumar? Audience, if you have any questions, you can unmute yourself and ask.
Hello, sir. Thank you for the presentation. Actually, how we observe the magnetic domains? Actually, we can observe it using the neutron scattering and Lorentz transmission electron microscope. Is there any method other than this which is available?
There are multiple methods. One is this Kerr microscopy, and the domain size is restricted by the wavelength of the light that you use. So you cannot image very small domains. The second one is magnetic force microscopy. You all have done atomic force microscopy, and there's something called magnetic force microscopy. Instead of atomic force, you map the magnetic force, and there you can have much higher resolution. So the magnetic force microscopy also can give you the domain information. The Lorentz microscopy, which you have already mentioned. There's something called SEMPA, SEM with the polarization analysis. For example, the electrons which are coming from the SEM in a normal SEM, if I do the polarization analysis of the electrons which is coming, you can also do the magnetic domain. And also something called the photoelectron microscopy, like you do XPS. So what you can do is that there also you can do a lot of imaging, photoelectron emission microscope, where you add the spin polarization, you can do the domain imaging. So there are different ways of doing domain imaging. The earlier days, what they did was they just sprinkled iron filings on something and looked at the pattern and found out. So from there, we have reached the stage that we can really look at very small magnetic fields.
Okay, sir. Thank you. Sir, what is the difference between the domains we observe in the bulk matter and the thin film? What are the
No, there is no particular difference, I would say. But when it comes to thin film, see why domains are formed, because when you have a single particle, and if you start, I mean, it has got a north pole and the south pole, it's a single domain. As you increase the domain size, the magnetostatic energy goes up. So in order to minimize the magnetostatic energy, it breaks into magnetic domains. So that's how magnetic domains are formed. Now, what defines the domain ball width is a competition between exchange interaction and the anisotropy. So that decides the width of the magnetic domain ball. Now, that is in the bulk. When it comes to thin film, even the dimension plays a role, because a material will prefer to get oriented in plane magnetized because to reduce the dipole field. Whereas when you become extremely thin film, an additional interface anisotropy comes. So compared to the bulk material, in a thin film, the dimensionality as well as the interface anisotropy is also adding to the domain dynamics. Because of that, the domain structure will be slightly different in thin films compared to the bulk.
Thank you, sir. Thank you very much.
Thank you. Is there any other question? Okay, if not, I will ask one question. Thank you very much, Professor Anil, for this very exciting piece of information based on this spin orbit torque controlled magnetization switching. So you have shown us this improving upon the current density values by 2 orders almost by carefully choosing these layers, right? So you have gone from the simple stacking of this PT-CO, PT, then tantalum PT-CO, PT, and then you have also introduced this ferromagnetic layer, right? COFEB. And you also told us about this having 2 opposite spinol angle materials for sandwiching. So now that you have done so many different stacking sequences and studies, do you have some very broad guidelines for improving upon this spin orbit torque efficiency?
Yeah, the thing is that now we are exploring the topological material, because materials with heavy spin orbit interaction. So now we are exploring the topological material which has got very high spin orbit interaction.
Okay.
And also, if we can, even further, we can tune this by tuning the interfacial properties. Finally, there's something called a Jabotinsky-Moria interaction at the interface. That depends on the interface quality. So we need to further improve the interface quality, and that's what we are trying.
Okay.
And moving towards fermions.
Okay, great. Thank you. I think Santosh has a question. Santosh, go ahead.
Anil, I just missed the talk for 5 minutes. So that particular sequence where we have the cobalt COFEB, which has created a gradient in the.
Yeah.
Can you hear me?
Yeah, I can hear you.
Yeah. So you have created a gradient. So how do you kind of using X-ray, how do you figure out whether that gradient is?
This gradient you cannot figure out from X-ray, but we know that, see, we deposit on a 1 square centimeter area, and then we do the patterning and then do the AFM at different points. And we know that from the left end to the right end, if I put 40 nanometers, it is 40 nanometer on the left end and 45 nanometer on the right end. That is coming by the geometry that we use for this deposition. And then if I scale the thickness down, you get the same effect there, because the thickness gradient will be there, but you are unable to measure that.
So does the magnitude of this gradient matter?
It matters, because if there is no gradient, there's no switching without magnetic field. And we are now, by the gradient, we can also find out how much the magnetization is tilting with an accuracy of 0.3 degree. If the magnetization is perpendicular, and if it is away by 0.3 degree or more, we can even measure by these techniques.
Okay. Yeah. So I saw your recent work on using similar ideas on spin reorientation in orthoferrites.
Yeah. Yeah.
I mean, I think similar work was there in 2020 by some other group, I think. Yeah. And I actually probably will discuss with you when I talk to you. Okay. Nice. Okay, that's it.
Okay, thank you. I think one more person has raised the hand. Swalihu, please go ahead. Unmute yourself and ask. Yeah.
Okay. Sir, what is the effect of magnetoresistance in the magnetic tunnel junction in this case?
No, here I'm not making a tunnel junction. See, this is just a purely, there's no magnetoresistance effect here. And in a tunnel junction, depending upon the magnetization parallel or anti-parallel, you get a high resistance or a low resistance.
Okay. Okay, sir. Thank you.
Thank you very much, Professor Anil, for the exciting talk. I will close this with a request that next edition of this conference, please arrange in person. Yeah, thank you so much. Yeah, I think now we will move on to the last speaker, Dr. Sinoy Thomas from Cochin University of Science and Technology. Dr. Sinoy has actually obtained his PhD from QSAT. So he has returned back to his alma mater to teach. And before that, he spent a couple of postdoctoral terms, one at the Chemnitz University of Technology in Germany. And then he served as an Inspire faculty, DST Inspire faculty at the CSIR NIST lab in Trivandrum. And apart from the Inspire Faculty Award, he has also obtained the SCRB's Early Career Research Award in the year 2018. And he also obtained this DAD Visiting Research Fellowship for the university scientists. And he has many publications ranging over wide topics. He started, I think, with the fabrication of thin films and nanostructures, amorphous alloys for his PhD, but moved on to work in spintronics, magnetocalorics, and most recently on magnetic vortices. So in today's talk, he is again going to touch upon this magnetization reversal, but in other materials, namely soft ferromagnets, okay, magnetic vortex systems. Over to you, Shinai. Thank you.
Okay. Thank you, Professor Nirmala, for the kind introduction. So it's clear, am I audible?
Yes.
Yeah, okay.
Very good. Yeah.
Okay,
thanks.
so let me congratulate the organizers and thank the organizers for inviting me to discuss some of my recent research results. So today I will be discussing with you about the non-collinear spin textures in soft ferromagnets. So according to World Economic Forum, the amount of digital content that was created worldwide last year was around 44 zettabytes. And this number is expected to get doubled by the end of this year. And most of us rely on a magnetic hard disk drive to store the digital information which we create. And a small introduction to the hard disk drive was given by Professor Anil Kumar in his last lecture. So I will be briefly touching about some of the few aspects as far as the hard disk drive is concerned in the first slide as an introduction. So this is a schematic of a hard disk drive which you could find in our desktop computers as well as laptops. So basically this consists of two main components. First one is a disk which could be rotated at a typical speed of 7,200 RPM. And on the top of the disk, you could see a needle-shaped sensor. This is basically the read as well as the write sensor. And if you have a close inspection on the disk, you could see that this is basically a magnetic alloy thin film which is deposited on the top of a glass substrate. And basically this magnetic alloy thin film is serving as the media where we could write our information. So for example, digital zeros and ones corresponds to regions where magnetization is pointing up or down. And specifically in a specific region, the information is recorded by applying a magnetic field using the right head. So as far as the read sensor is concerned, so it basically works on the principle of giant magnetoresistance or tunnel magnetoresistance, where the resistance of magnetic stacks changes once the magnetization direction of the adjacent ferromagnetic layer changes. So, so it means that due to the increase in the volume of the digital content which we create in our day-to-day life. One have to go for hard disk drives which have more areal densities, and current requirements forces us to increase the areal density of hard disk drives to more than 2 terabit per inch square. So there are several strategies developed to address this issue, and one such strategy is to use the so-called bit pattern media, where one lithographically define magnetic islands on the top of this disk, and each of these islands act as a single bit, and depending upon the magnetization direction, one could define the digital zeros or 1. So typically, these islands are made from magnetic materials having uniaxial anisotropy. And as far as magnetic materials with the uniaxial anisotropy is concerned, so if the magnetization direction has to be reversed from one particular direction, let's say from the top orientation, bottom orientation to the top orientation, then the system has to overcome an energy barrier. And basically this energy barrier is a product of a uniaxial anisotropy constant Ku and the volume of the material. So it also means that one could not simply reduce the volume of the magnetic island so as to increase the areal density of the hard disk drive. The reason is that if you decrease the volume below a critical volume, then what happens is that the anisotropy energy barrier Kub will now get equated to the thermal energy KBT of the system, and then the thermal energy will be sufficient enough to flip the magnetization direction. So it means that if you decrease the volume below some critical volume, then the magnetization within these individual elements is no more thermally stable, or one could say that the information which we write is no more thermally stable because of the dominance of the thermal energy. So this is a serious issue which is well known as the superparamagnetic limit in the magnetic recording industry. And so people have developed several strategies to overcome the superparamagnetic limit. And so one currently pursued topic is to investigate non-uniform magnetic states in ferromagnetic systems. So in this slide, I have shown few examples of non-uniform magnetic states, which is possible to observe in magnetic nanostructures. The first one is the so-called magnetic vortex structure, where the spins will be curling in the in-plane direction. And at the center of the structure, the magnetization will be pointing perpendicular to the plane of the structure. So we also have the bubble magnetic states, as well as the skyrmions, which are basically topologically protected. So skyrmions is one of the hottest topic which is pursued by several scientists all over the world. So today's talk, I will be focusing on our recent results in magnetic vortices, how one could stabilize magnetic vortices in magnetic nanostructures, and how the magnetic vortices evolve with an applied magnetic field as well as an external temperature. So before going into more details about the stabilization of magnetic vortices, let us consider a soft ferromagnet, which is very small in size, typically, let's say, tens of nanometer in size. And basically, the spin configuration in a ferromagnet is basically due to the minimization of the total energy of the system. And in a soft ferromagnet, if the size is in the range of a few tens of nanometer, then the exchange energy will be dominating and the system will be in a single domain state. And however, if you increase the volume of the soft ferromagnet, let's say, if you increase the size to few micrometers, then what happens is that the magnetostatic energy basically increases. So since the magnetostatic energy is the volume dependent energy parameter, so magnetostatic energy increases. And in order to minimize the magnetostatic energy, the system will get subdivided into different domains, which is separated by domain volts. So in the left side of this, right side of this slide, you could see a closure domain, which is typically observed in a soft ferromagnet with a cubic crystalline structure. And So basically, in short, one could conclude that domains are basically formed in order to minimize the total energy of a ferromagnet. And there is a good possibility to observe non-uniform spin configurations in a transition region in between the single domain region and the multi-domain region. So for example, if you take a disc-shaped ferromagnet, which is having a typical diameter of a few hundreds of nanometer and a few nanometer thick, then there is a good possibility that the spins could curl in the in-plane direction. And at the center of the disk, in order to minimize the exchange energy, the magnetization could point in a perpendicular fashion, perpendicular to the plane of the disk. So the in-plane circulation of the spins is called the chirality, and out-of-plane magnetization located at the center of the disk is called polarity. And basically, this is the core. This is basically a magnetic vortex structure with the core magnetization exactly at the center of the disk. So now if you measure Z component of magnetization as a function of position, then one could see that there is a large values of Z component of magnetization due to the magnetization from the core of the magnetic vortex. So now, depending upon the sign of polarity and chirality, 4 different states are possible in a single element. And this is very important as far as high density storage is concerned. Okay, so now now the question is how one will realize vortex structures in nanostructures. So typically one goes for lithography techniques where one could clearly define magnetic islands of some specific diameter and thickness. But you know that the lithography technique is a time-consuming process as well as it's not cost-effective. And so then we thought of combining a self-assembly technique with thin film deposition to realize the magnetic vortex structures in magnetic nano islands or magnetic nanostructures. So, so for that, we started with preparing a template. So basically, our template is a long-range ordered SiO2 nanospheres, which is self-assembled on the surface of a silicon substrate. And for preparing the SiO2 particles, we adopted the so-called Stauber process, which involves the hydrolysis, condensation, and polycondensation of tetraethyl orthosilicate. And depending upon the PEOS concentration, it is possible to realize the silica spheres of different diameters. And once the particles are obtained, we self-assemble it on the surface of a silicon substrate. So where it is possible to obtain long-range ordering of SiO2 spheres. And once the template is ready, then we take this template to a DC magnetron sputter deposition system where we deposit soft magnetic thin films onto the top of this self-assembled SiO2 nanoparticles. So here shows a schematic of the scanning electron micrograph of samples such prepared, and one could see a long-range ordering of SiO2 particles. And if you look at the cross-sectional EM image, one could see that on depositing the thin films onto the surface of the spheres, actually there is a good possibility to obtain the so-called magnetic cap-like structures. So where we have a maximum thickness at the center of the pole of the cap, and as you go on to the ridges, the thickness will be shrinking, so that one could realize magnetic nanocaps on the top of the SiO2 nanoparticle arrays. So there is a good possibility to stabilize magnetic vortex structures on these magnetic nanocap structures. So a schematic of spin configuration adopted by these soft magnetic nanocap structures is shown here. So here one could see that at the ridges of the cap structures, the spins will be curling in an in-plane fashion, and at the pole of the cap, the spins are pointing in a perpendicular direction in order to minimize the exchange energy. So now if you measure magnetization as a function of field curve for an assembly of such magnetic nanocaps, soft magnetic nanocaps, then you could end up with a loop which is something similar to the one which I have shown here. So here basically, if you decrease the field from a positive saturation and at some intermediate external magnetic field, there is a drastic reduction in magnetization, and we will really end up in negligible remnants. So this strong reduction in magnetization at intermediate fields is basically due to the nucleation of the non-uniform magnetic vortex state. And once you increase the field in the opposite direction, the magnetic vortex will get annihilated from the system, and the system will be tending to a uniform state in the opposite magnetic direction. So the spin configurations are schematically shown here. At very strong positive field, it is possible to align the magnetic moments of the cap structures along the field direction. And once you decrease the field and reaches the nucleation field, you could nucleate the magnetic vortex. And once you decrease the field to zero, the core of the magnetic vortex shifts to the center of the cap structures. And once you increase the field in the opposite direction, the magnetic vortex core will get annihilated from the system, and you will get a uniform system, uniform spin configuration, which is saturated in the opposite field direction. Okay, so we also routinely do magnetic force microscopy to have more information on the spin configuration in such magnetic nanocap structures. So here is a MFM image, which is recorded on a 330 nanometer SiO2 spheres, which were deposited with 30 nanometer thick permalloy thin films. And one could see that at the center of these spheres, or at the center of the cap, there is a contrast. So basically, the MFM is sensitive to the stray field, which is directed perpendicular to the plane of the sample. And so basically, this contrast is arising from the core magnetization. So one could see the bright contrast as well as the dark contrast, so which actually means that the core magnetization which is pointing up or pointing down. Okay, so so the initial experiment was to investigate the stabilization of magnetic vortices. So for that, we deposited 4 nanometer thick iron onto the top of SiO2 spheres, thereby forming iron nanocaps. And so we recorded magnetization as a function of field at the different temperatures, and we extracted the nucleation as well as the annihilation field. And what we found is that in this particular sample, the nucleation field is around 25 OSTER, and the annihilation field is around 60 OSTER. So then we coupled these iron nanocaps with an antiferromagnetic iridium manganese. 5 nanometer iridium manganese was deposited onto the top of this 4 nanometer iron, thereby coupling the magnetic vortices with the antiferromagnetic iridium manganese. By keeping in mind that by coupling with an antiferromagnet, it would be a useful tool to stabilize the magnetic vortices in an external field. So here is the moment as a function of field curve for such an exchange bias system. So where one could see that the nucleation field is now increased to 250 OSTER, and annihilation field is now increased to 500 OSTER, which means that the coupling with an antiferromagnet really provides the field stability to the magnetic vortices. Okay, so we also did a series of experiments by changing the thickness of the magnetic nanocaps. And what we found is that, so for example, if you increase the thickness to, for example, 70 nanometer, then there is a good possibility for the coupling of the nearby magnetic vortices. So we call this as basically the exchange coupled magnetic vortices. And in order to understand the magnetization reversal in those exchange coupled magnetic vortex arrays, we did a magnetic transmission X-ray microscopy. And what we found is that here the reversal process is via the nucleation of a collection of magnetic vortices rather than individual nucleation of magnetic vortices. So this is what you could basically see in this MTXM image, where one could see at the switching field a large domains of vortices with a similar polarity as well as chirality is present. So this is basically due to the exchange coupling between the nearby magnetic vortices. So as a next step, we wanted to investigate the influence of temperature on the magnetization reversal process. And for that, we chose iron palladium alloy system, and we deposited an array of polystyrene nanoparticles, which is having a fixed diameter with iron palladium thin films having different composition with a thickness of 20 nanometer. So here shows the scanning electron micrograph, which shows the ordering of polystyrene spheres onto the top of a silica substrate. And onto the top, we have deposited iron palladium alloys, which is basically forming the so-called magnetic cap structures, which one could evidence from the cross-sectional transmission electron micrograph image. Okay, so we did experiments with iron palladium alloy having different compositions with the iron percentage ranging from 30 atomic percentage to 20 atomic percentage. So we did this experiment so as to tune the Curie temperature so that one could tune the exchange energy associated with these alloy thin films. Okay, so in order to have a more insight into the temperature dependent reversal process, we did first order reversal curve measurements using a magnetoptic Kerr effect system at different temperature. So here is a summary of two different temperature at T is equal to 250 Kelvin as well as 345 Kelvin. And at 250 Kelvin, one could see that the switching from the single domain to the vortex state involves an energy barrier, which is basically resulting in an hysteresis in the Kerr loop. So, however, if you increase the field temperature to 345 Kelvin, then one could see that there is a hysteresis-free switching. So basically, it means that now the energy barrier for switching from the single domain state to the vortex state is overcome by the thermal energy of the system. So in order to have a more understanding about the temperature dependent reversal process, we recorded the nucleation as well as the annihilation field as a function of temperature. And what we found is that above a particular critical temperature, the nucleation and annihilation is nearly overlapping, which means that above this particular critical temperature, thermal energy will be sufficient enough to switch, the single configuration from the single domain state to the vortex state, or one could have a possibility for observing the bistability of the magnetic states at temperatures above this critical temperature. And this critical temperature we label as the bistable temperature, above which we could observe the bistability between the magnetic vortex state as well as the single domain state. So we did micromagnetic simulations to have a more understanding on the energy involved in this bistability. So what we found is that at intermediate field, the energy barrier for the switching from the collinear state to a vortex state, as well as the vortex state to the collinear state, is nearly equal. And if you supply the thermal energy which is sufficient enough to overcome this energy barrier, then there is a good possibility to observe a hysteresis-free switching in between the collinear and the vortex state. So we extracted the bistable temperature for iron palladium alloy with having different composition, and what we found is that the bistability temperature T is increasing as you keep on increasing the iron content in the alloy. So this is basically due to the fact that as you increase the iron content in the alloy, you are basically increasing the exchange energy. So thereby you are also increasing the energy barrier. So we have to supply more thermal energy so as to overcome this energy barrier. So that's why T is increasing as the ion content in the iron palladium alloy is increasing. Okay, so as a next step, we try to investigate the influence of shape anisotropy on the magnetization reversal process in these magnetic nanocap structures. So we did a series of micromatic simulations for both symmetric magnetic nanocaps as well as asymmetric magnetic nanocap structures. So a symmetric magnetic cap structure is characterized by a maximum thickness at the pole or the center of the cap, and a asymmetric cap structure is characterized by a maximum thickness at a degree of at an angle of 20 degrees from the perpendicular. So we did simulations for different thicknesses, and so the results are summarized here. So here is the simulated MH curve for symmetric caps for having different thicknesses, and by applying field at along X as well as the Z direction. So what one could see here is that the loops are overlapping for the measurements by applying the field at different directions. So it means that the MH loops are nearly direction independent, so which clearly indicates the symmetry associated with the system. Okay, so now coming to the asymmetric cap structures. So if you apply field along the X direction and measure magnetization in the X direction as a function of the external field, then one could see that if you keep on decreasing the field at a particular intermediate field, there is a drastic reduction in magnetization and negligible remanence and the coercivity. And at very high field, the system is saturating in the opposite direction. So in order to have a more insight into the reversal process, we recorded the spin configurations at different fields. And what we observed is that at very high positive fields, the system adopts a onion spin configuration. And once the field is reduced, then the system turns to a C state, which is basically arising due to the shape anisotropy associated with the asymmetry of the system. And so now you increase the field in the opposite direction, a reverse onion state is obtained. So, so it means that in asymmetric system, due to the shape anisotropy associated with the asymmetry, so it is really influencing the magnetization reversal process. And in order to investigate the shape anisotropy in the system, we applied field along the Z direction. And what we found is that the reversal is typical of a reversal via coherent rotation of the spins. So this basically tells about the shape anisotropy associated with the asymmetric system. Okay, so what we understand is that one could carefully tune the magnetization reversal process by just changing the asymmetry associated with the magnetic cap structures. So we are also interested in investigating the 3D magnetic vortex spin configurations in spherical nanoparticles. So this is very important as far as the self-assembly of these nanospheres, ferromagnetic nanospheres is concerned. So depending upon the available entities, one could result in a chain like morphology or a triangular shape or a Y type or a square shape. So basically the assembly is driven by the stray field associated with this 3D magnetic spin configurations in this spherical soft ferromagnets. So we also performed micromagnetic simulations on spheres, iron spheres having different radius ranging from 10 nanometer to 25 nanometer. So what we found is that at a very small size, the system is in a uniform state, and if you increase the diameter, then there is a good possibility for nucleating a magnetic vortex spin configuration in this spherical nanoparticles. So we also simulated the magnetization as a function of field curve for a single spherical particle. And what we found is that if you decrease the field from high positive values, Then at an intermediate field, you nucleate the 3D vortices with the core of the vortex pointing along the field direction. And if you keep on decreasing the field, the size of the vortex core decreases. And at one point, the vortex core magnetization flips, which is basically resulting in a hysteresis in the MH curve. And finally, if you increase the field in the opposite direction, the core magnetization or the size of the core increases. And finally, at 0.6, it will get annihilated from the system, and we have a single domain system which is saturated in the opposite field direction. Okay, so as a summary, we have seen vortex structures in nanocaps, which could be considered as a two-dimensional magnetic vortex structures, where one could see that if you apply a field along the in-plane direction, there will be negligible remnants and coercivity. And basically, once the vortex core is nucleated, it is moving perpendicular to the direction of the field. And in 3D vortexes, due to the flipping of core magnetization, there is a possibility to get a hysteresis in the MH curve. And so this is one of the characteristics associated with the 3D spin configurations, where the core magnetization is pointing along the field direction. And if you decrease the field and increase the field in the opposite direction, the core magnetization will flip, and this will be eventually resulting in an hysteresis. Okay, so with this, I conclude my presentation, and I thank you everyone for your kind attention.
Thank you very much, Dr. Shinoy, for keeping up the time, as well as for giving a very insightful presentation on this latest topic. Audience, do you have any questions for Dr. Shinoy? If you have any question, kindly unmute yourself and speak up. I think Dr. Solihu has raised hand. Please go ahead.
Hello, sir. Thank you for the presentation.
Hi.
Actually, I want to know what is the effect of Hall effect in the Fermion structures. I read about using the antiferromagnetic structures have more advantages over these fermions, since these antiferromagnetic structures overcome this Hall effect, right?
I am not quite sure about the Hall effect measurements in Fermion systems. Probably I am not an expert person to discuss about this.
Okay, sir. What about the dynamics of these structures or the fermions? How it transforms?
Yeah, actually, people are also looking about the dynamic properties, especially for applying this for generating, for example, the magnetic vortex structures could be used as the core oscillators for realizing the oscillators. So basically, so this is also a well-studied field. So one could apply a field and to see how really the core magnetization is processing according to the strength of the applied field. So there is also a good possibility to investigate the dynamics, but I haven't looked up on that yet.
Okay, sir. One more question. What is the application of observing the fermions in bulk matter?
Yeah, so basically, the advantage of fermion is that they are topologically protected. So it means that mathematically, the turning the topological object from one topological state to another involves an infinite energy barrier. However, in real systems, the energy barrier is finite. But still, since the energy barrier is very high, this is well sought for the so-called magnetic recording applications. For example, in previous racetrack memory, one was basically utilizing the movement of domain walls. So now one could utilize the movement of skyrmions for storing the information. Yeah.
Okay, thank you, sir. Thank you very much.
Thank you. Any other question to the speaker? Okay, Shinoy, I want to ask you one question. You emphasized the important role of the shape anisotropy, right? In the magnetization reversal. Did you also look at other structures? I think primarily you have shown us this spherical thing, but did you also?
Actually, our focus in this particular work was basically on these cap structures. And you see, so basically our aim from the experimental point of view, our aim was to, do some oblique angle deposition so that one could tune the shape anisotropy associated with system. And one problem which we really face is that, the vortex nucleation is random. So if you look at the MFM image, at one point, the core is pointing up and another point and it is down. So somehow by tuning the shape, is there any possibility to tune, collectively nucleate the vortex system or to control the chirality and the polarity? So this was the experimental motivation. So before that, we did some simulations, and our simulations show that it's really promising to tune the shape anisotropy and to control the chirality as well as polarity in these systems.
Okay. Thank you very much. Yeah.
Okay, thank you.
Yeah, thanks.
Thank you, Professor Nirmala.
Yeah, thank you, Shinoy. And I would like to thank all the speakers of this session for the very informative set of lectures. And I also thank all the audience here because they have patiently sitting through the entire session. And what is more, we have more food for thought along with your lunch. Please go through the poster session of this magnetic materials topic. There are about 13 posters, I think. You should go through that and give your feedback and suggestions to the presenters. Okay, thank you very much. I give the mic back to the organizing committee.
Right, ma'am, thank you. The session has come to an end. My sincere thanks to Honorable Chair, Professor Nirmala R, for conducting the session. A heartfelt gratitude to all our speakers, Professor S.M. Yusuf, Professor Santosh PN, Professor K.G. Suresh, Professor P.S. Anil Kumar, and Dr. Sinoy Thomas for their remarkably comprehensive and fascinating talks. This has been a very interesting and informative session. Again, I extend my gratitude to the active viewers and listeners for making this a lively event. We will now have the poster presentations on the topic magnetic materials. In order to attend the poster session, please visit the conference website or follow the link that will be available on the chat box. Poster presenters, please also note that an expert committee will be reviewing all the posters displayed on the website. After the poster session at 2 p.m., we move on to the 3 parallel sessions of oral presentations on the topics energy materials, biomaterials, and other materials. Please visit the program schedule to obtain the links for your respective sessions. Before leaving, we also request everyone to fill the feedback form available on the chat box. Thank you all and good afternoon.
Thank you.
Hello, ma'am. Poster presentation.
This poster presentation is through the conference website. You need to visit the conference website for poster presentation.